Yeah, got it. Please install the software in the meantime, and then you have to email me the site key, and good morning, sir. And I give you the license. So there are a few examples, like you start, some of it is software, some of it is Excel. Like it's not just about understanding this Eushaw dynamic software. It's all about understanding how to design the steps are for like wellboard design, simulation. And so the whole thing about this course is not just the software thing, is like 70% is software, but it's 30% to understand what's the background is also. Like then if you have a background of what's going on, it's give you the confidence about using any software. And that's not separate from the other softwares. That's pretty much exactly the same type of thing. So just give you an intro about like myself and this. We started software about 2019, and initially was focused on horizontal wellbore design, with having the near wellbore communication with the reservoir, and then it expand on. And if you hopefully I can another time, or I do this through Zoom in 6-7 months, and I teach you guys the shale oil module, which has a fracture and stuff and all those stuff. But now this one is mostly focused on conventional part of the software, how we do the wellbore design, how we do the whole reservoir simulation with the wellbore effects, and what other things are different in this software than other softwares, and what sort of a designs that we are looking to do with this software. Like every software has its limits and boundaries and advantages and disadvantages. And so we have to understand what are those limitations are. And so exactly like other softwares. So please install it and send me the site key. Then we skip this example, and then we go and do a few PowerPoints, like slides on inflow control devices or flow control devices. And then once everyone's had the site key and activated license, we do the first example. So, and then at least we know why we are doing these steps, like why we have to do this stuff. Okay, there goes the first one. Okay, so first of all, let me explain the inflow control device or flow control device, because mostly I teach this part of a course or this software in like the conferences on SPE, which is really focused on inflow control device. So now I think a few of you guys probably know what the inflow control device is. So it's for the people in Aberdeen, for example, or people in Middle East, like working in offshore, or people in Gulf of Mexico, that's not something that they haven't heard. But for the people probably in North Dakota or Calgary or the other parts, it's maybe have to give you some kinds of description. So in horizontal wells that we do design, especially in offshore and also in not the shale regime, but in the conventional world and also in the thermal assets, we have a lot of hydraulic issues. Like we have a toe to heel caulking. So you produce more from heel, you produce more from toe, unconformance of the wellbore affecting our production, especially if you do water flood, for example. If you do water flood, you see the water coning come. So there are tools which becomes pretty much a standard these days, and we call it inflow control devices, which some sort of a restriction against the flow driven by density and viscosity. So if there is a gas which has a lower density and is unwanted fluid, you choke it more. If it's a viscosity, a lower viscosity like water, which is unwanted, you choke it more. So these are really small things you put on, like for example, on liner deployed type stuff. There are like, it can be different types, but one of them is Venturi, and you put it on here, and is the delta P happens at these chokes. That's probably control the unwanted fluid, but there are so many design aspects of it. And we have two sort of ICDs or OCDs or FCDs, one for inflow on the producer and one for outflow, which is OCD. So really the basics of these things on the Venturi part is follow with the Bernoulli principle. What Bernoulli principle says is like pressure plus the momentum, density times velocity square, it has to be constant. Okay, that's a Bernoulli principle. That's a principle that how airplanes actually works. Right? Anything, there are a lot of things around us works based on that principle. But these Venturi FCDs also works based on this. So if you have a higher V and on the throat, you're increasing the velocity, you dropping the P because that whole thing has to be constant. And because the V has the velocity have the power of 2, then you choking the pressure more and more. So these things really works like this. You have a P up and you have a throat, and then you have a P out. So, and it's really a function of this geometry of the Venturi that we have. So it's not just simple equations. Normally doesn't work. You have to do kind of a CFD example, CFD simulation. So that's why the first example that I have it, hopefully everyone install it and then I can provide you guys site is about how to do the CFD and how this software connect the CFD to wellbore and the wellbore design and doing all things together. If you guys are from shale oil world and talking about the perforation erosions, that's a big topic these days on the shale oil world and the proppants coming. That's exactly the same thing. And you see a lot of academics really these days working on understanding. It's not a simple equation that you can just put it like CD of one number. You have to do CFD to understand these phenomena. And that's exactly this. So this is nozzle formula. This is nozzle or Venturi formula. And there is a term CD, which is discharge coefficients, and the number change between 0 to 1. And depends what shape you are, you have a different CD. So really delta P or the choking is a function of density, the rate or velocity, area, if you put it like area, because you have to talk about velocity, so you have a rate, then you have to divide by area. So let's do example 2, and once we finish it, in meantime, hopefully everyone have the software installed, and then I can provide you guys site view, and then we go back to the software. But the first example is just Excel spreadsheet, and let's do it. And in the meantime, hopefully everyone's have software. So Jawad send you guys the rare version of the visa stuff, and hopefully I send you guys example 2. You don't have example 2. Please send you example. Let me see. No. I just send you guys the examples regarding the software. So let's have the software installed, and I give you guys site key, and then We can do it. I find the example too for you guys. Let's install the software first. Right now. There we go. You guys know which email you guys have to send me? So once you install it, there's a site key, and you copy it and you send it to me, like Mazda.Irani@Energy. Let me write it here and here, and please send it to me. Let me just do it here.
Yeah, this is the Windows application, so.
I'm not able to use the software.
Oh no, you wanna? Oh yeah. Okay, so you use like there are a few software working on Mac. Not engineering software is working on Mac.
So let me consider do it again.
Yeah, so you send this site key to me, and I think Java sent it to me, and I didn't.
Why the email?
Yeah, send me through the email. And, let me see. So this is the serial number that you have to send me. No, that's not the serial number. The site key. Email me, and I give you license. The email again.
Also, you can hear on the Zoom. Yeah.
That's my name. I have to put it on. You guys send me on the good morning, sir. And then let me do it for Java. Oh, Java, you sent me the wrong psyche. What you send me? Is this one you got? No.
Let me send it again.
Have to put it like shouldn't be like this. Like what's site code? Oh, you put a. Don't put dash or anything. This is the thing I need.
Okay.
Did you send me that? No.
Let me send it again.
No, you didn't send me that. Like it's you send me the serial number. Don't be sending the serial number. Just copy paste. Let me just make it bigger, guys. Now you see it. Yeah. Install it first, and then it takes like 30 seconds to install. Send me again.
Yeah.
You guys have it now. I give them. I get the. Okay, George's got it. Let me get it to George's first.
Yeah. Okay.
You get it faster than okay. George's, and we provided to him. Okay, George's, you got it now. Hopefully George's is here. Java, you are next.
Thank you.
Next is the P. Okay, the P, got it. Okay. Any more? Only 3 people send me. AP is your name?
Yes, it's me. I got
AP is yours?
Yeah.
Got it. And it's working now?
Yeah, so it's
Emmanuel, did I respond to you? No? No. Okay. No, you have to put it there and you submit. Like, what's your name? Like, man. Just copy here. You have to submit. There is a button on the side. Submit.
Does it install immediately or gonna wait for a couple of minutes?
No, you install it.
Yeah, because it's showing that authorization not.
No, you install it first and then you give me. Oh, you have to send me that. Oh, so what you send me?
You reply to us.
You put it there, copy paste it there, and then hit the button there.
Okay.
No, okay. Copy.
Submit.
Register license. And now, okay.
The secretary on here.
All right. Hopefully, yes. How many got it?
I'm still downloading.
You send me anything or no?
I'm still downloading.
He's downloading the software.
Oh, you download it. Okay. You have to register. There is a button on the next. You register. Did you send me the?
I'm good. Good.
There it is. There it is. So you copy paste it in the place on the bottom. And it's on.
So we have the username of the organization on that. There's no. For the organization of it, just UND or
Huh?
for the organization.
That doesn't matter. Like you just put whatever you want. Like you put NASA or whatever you want. Just give it everything. Okay. Yeah. So send me again, judges, and then don't hit anything like once you do it.
Yes.
Keep your names. Just look. No, Luke, you sent me wrong thing. Luke, you put a dash in between yourself or what? So what are you sending me there? That's not the right one. It shouldn't be any dash. Like it should be a spaces. Who is Luke? You? Let me see. Send me the wrong.
What we're standing. What should I do next?
Yeah, okay. Send this to me.
Okay. Just that. Send me that one.
Friday. Friday.
Friday?
Yeah, my name is Friday.
Next Friday, and he said me something like I said, like teaching on Friday. I said like I'm here on Friday. Yeah. Oh yeah. I closed that one. Let me open it again.
Yeah, no problem. I think it's done. Because it is something,
Friday. Check and generate copy. Okay. Friday, you have it now. Let me see. Side code for judges. There are two judges or what? Judges. Two.
next. Not enough.
You have to install it first and then you get this. Okay, hopefully look again.
Nothing down.
Okay, there are two looks too. Check look number 2. Generate. It has to work, man. Like it. No, you can have a USB and install it. Yeah.
Showing the file as properties that cannot be copied.
Oh, you want me from USB? Oh, I don't have it on USB on myself. Do it and then you skip the first example and then. Okay. How many people can run it now? Like at least half?
Change the same code again. The same code and the
So what do? You copy paste it there and hit the register? Yeah, I have to come and see what you've done. But how many people has it? At least half got it. For those people got issue, like let us run one example and then you see the other thing. And then I come and see. We probably have to uninstall it or I don't know what's going on, like on your side.
So can we ask online students if they have installed the software or they have it? So online people, can you hear us?
I just sent you.
I sent you. Look, I sent you.
Yeah.
Super.
Huh?
Video is from Malawi.
It's about it. Like,
I don't see your email, man.
is it a movie?
Yeah.
Even you are on.
Where you send it? You send it to someone else, man. You send it to. You have to send it to this.
Did you send it to that?
Yeah, I guess so.
Yeah, I did.
But you check again.
Like this is my email. I don't see yours.
Then ask them.
Okay, everyone on the other side on the Zoom. You guys
Yeah,
install
I
it.
think you are on mute.
Yeah.
On mute.
No.
This one I think was something different.
I don't know as people online. Yeah.
This one was something
They say
different.
that.
The previous one.
Like, no one is online.
There are 3 people I know at least on the Zoom. I don't know how many people I have.
Yeah, this is.
Oh, I got it now.
Yeah.
Alan?
Yes.
Okay, let me see. It's
Yeah, all from.
say oh, okay. Here is your sound, and this is your address again. Yeah, I send you, but it's probably some issue with you have to uninstall it and then do it. And then I see what's going on. Maybe you have something there that doesn't. I give you. Okay.
We take register license.
Register license and then okay. Other than judges and the people on the other side, the people on the did you install the software? That's Java. Okay. So hopefully people on the other side please install it. Give us and there we go. And judges on the break, I'll talk to you and see what's going on. So I forgot to put the Excel on this thing, but we have it here. So for all of us, I forgot to give you that table. You just create this table in Excel. So that's how the software works. Yeah, you have to give it, just have it in Excel, these dimensions. Let's do it. I thought I'd give you the table for it, but I didn't. Okay. So it's 0 is 0, 2, 4, 6, 14, 80, 80, 80, and it's 13, 6, 3, 2, 1.75, and the units are in millimeters, 3.5 and 30. Okay. You have it in your PowerPoint slides also. So yeah, so just do those and you copy it. So open your software, whatever, for those who install it already. So we want to do simple CFD, and then we connect this to the wellbore, and then connect the wellbore to the reservoir.
We didn't see the Excel sheet. Yeah.
You don't have Excel, like I said, like come to this and put these numbers in the Excel, like the way I did it. Okay, just do it. And then I do it twice for you guys. You come to flow control devices, you say add SCD, and you come over here, then you go to the model, and here you say computational fluid dynamics, and whatever you have in Excel, you just get it, copy, and you come over here and paste it. This is like this shape. Like we want to model this shape. Like you can put any numbers you want. Like, but these are, for this example, we want to do this, okay?
So it's start with the new things.
No, no, no. I'm fine with everything. Oh, pizza is awesome. Yeah. 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 Okay, so So once you do that paste, you see something like this. And this is Venturi, or this is like these stuff, very small nozzles. And these are, and you see the millimeters and stuff, like that's the sizing. You have a size of 2 millimeter at this point, and normally they have it this size. And you can come over here and play with these stuff, but don't do for now. So I just give you a brief description of what's going on, the background, because I'm not teaching those aspects. How many of you familiar with CFD, computational fluid dynamics? At least know the term. Yeah, you've heard. There's a famous software named ANSYS. What software? It's a huge software, but it's really hard, and it's not many people. That's why it's not very hard. Like in petroleum, like few people running it, and so that's the problem. Like there are so many aspects in oil and gas that we need to do CFD, but we are not doing it because there are applications like ANSYS. It's really hard to do it, and it takes for a long time to run.
They don't find anyone.
It takes time. Okay, so this software, one of the aims of this software, there are like 4 or 5 milestones in this one, but one of it is to have a CFD simple for the people in oil and gas and connect it to the other portion of the reservoir and wellbore that we want. So ANSYS, you do like normally the people like the hire 2 PhD mechanical in these service providers, and they come and sit and takes them 6 months to model this Venturi with a lot of convergence issue. And they make the tables, and the tables they convert to the equation, the equations convert to something, and they put it in the wellbore. And it's like a year of program. But it shouldn't be that long. Okay, so one of the aims of this software is whatever shape you want. Our examples that we deal with in oil and gas, there are few that have been handled here, but like a prop and transport in fracture modeling, for example. That's one of the key things that no one do CFD because the fracture software doesn't do it, but we have to. So now this example is on inflow control. So we try, one of the aim of this software is like to make the CFD simple for people and faster for people for the specific application. So you cannot go and design the airplane wing with this software, but you can design a oil and gas aspect. So this is like specific for this stuff. So let me just give very brief understanding on the CFD and what people does. So in flow control device, everything is a function of Reynolds number. So who doesn't know what's Reynolds? Everyone knows what's Reynolds. Yeah. It's a dimension number, rho VD divided by mu. So everything on the flow, if it's not relevant to Prandtl number, not relevant to the Nusselt number, then those are stuff always related to Reynolds number. So always, okay. So what we do in the world of the CFD is also Reynolds is a key important. So now we want to do the CD, which is the discharge coefficient. And this is not the one number. If you talk to the perforation guys in fracture modeling, they say 0.8, one person say 0.7, but this is not one number. It's related to Reynolds. And in the CFD world, there are so many different ways of solving the problem. One is just Navier-Stokes stuff, and one is the turbulent stuff. Once you get to the big Reynolds number above 4,000, you cannot use the old type equation like a Navier-Stokes. You have to do something different, like 4,000, 3,000. So that's what we have it here. You have it this, you see, you have a 4,000 here. So any software like ANSYS, us, and everyone's, you have to tell software when you want to shift from Navier-Stokes to something more advanced, because the formulation is totally different. There is no algorithm tells you when you have to do. It's always based on aspects of that problem that you're having. It's 4,000, 3,000 something. So you put it here, and then I'll just give you a brief understanding. There's a K epsilon and K omega. Most famous one is K epsilon method that people does. And if we go to the more advanced software like ANSYS, they provide different types of like parameters. You can use those ones, but if you're a student and you want to use your own stuff, you just put it off. So once you put all those stuff and you don't do the cavitation here, you just come over here and you just, after you put your table here, really, you don't do anything and you just hit the start simulation. Okay, that's it. And you wait like 7-8 minutes, and the software goes and run different Reynolds on this Venturi and provide the tables for your wellboard design.
Kind of sensitivity, you know.
Yeah, you can do anything, but for the wellboard design, you have to have tables based on Reynolds for the CFP. Then the wellbore model need that Reynolds dependent correlation to have it talk to the reservoir. Okay. So forget that one, then leave it there. Don't stop it. Like it's a CFD is, if you run this with ANSYS, you have to wait 2 days. But because we kind of do the grading, everything very optimized for this problem, ignore a lot of secondary functions, make the CFD faster. Okay, now go back to your thing. Oh, you have it installed. Let me get the Abdul Hakim. You're from Algeria too? Okay, good. So either Algerian or Ghanai, huh? That's how the North Dakota University works. And you're from Bangladesh. Okay, good. And you're from Russia or Ukraine?
I'm a Russian.
You're Russian. You're Algerian. Look Russian. Your accent is Russian too.
Yeah.
Abdul Hakim. Okay, Abdul Hakim, you have it now. Okay. Only Georges doesn't have it. Or you have it now? Okay, we have to see how it goes. Okay, let's go. Let's ignore this example because I forgot to provide it to you guys. And then hopefully we have this example one ready, and then we can talk about it. But it's a flow control device. Yeah, you can call it controlling, but it's that's ICV. That's ICV, which is you can't control the sizing. And those are more like ICV, which is like a valve. These are not choking or anything. They're the same shape, and you put it based on your well design, and you control the performance. You design it once, you can't change it. ICV, there's other thing that you can change it. Okay.
The software
Handle ICV, yeah. But yeah, not many people does ICV, but Norwegian does. So once we design it, then once we run the simulation, then we can come and see these stuff. But let's go talk about these stuff. Then we go more on the, yeah, it takes all of my CPUs, so I can't. So So let's go on this. So there is a paper, I forgot to send it to Jawad, but I send you in lunchtime. So that's what we publish on this. It's about different shaping and different things. Like the whole point of the modeling, once you go to the CFD, it's not just doing the CFD, and you have to connect this to the wellbore and reservoir design, and then see how the performance is helping you. Okay, so we have a Venturi A, Venturi B, and Venturi C, and the shapings are like this. Okay, Venturi A is this one. Venturi C is exactly the same shape, but you have it instead of 1.75, you have it 1 millimeter wider. But Venturi B is exactly this shape, but we have expanded. It's a longer one. Okay, so you just want to see how the different behaviors are different. You see the CD of A and C. A and C, the ones just have a throat size change. It's just shifting, but the whole shape is kind of constant. But the thing is, Venturi B is totally different. So the length of these devices quite important on their performance rather on the throat size, on the CD performance. So once we run this thing, and it's normally I run it before running the class. So now we do it in between because we didn't have a licenses. But once you do it, you see the like here, you see the CD or the discharge coefficient is not one number. Okay, so if you want to run any software and you ask for one number, that's not correct. And you see the changes are huge. Like, for example, for this thing changing between 0.7 to some numbers like 0.1. Okay, that's happening on every nozzle. If you design a perforation, it's exactly the same thing. If you're in the shale oil world, this is not just one number. It's a variation of the number. So that's a key finding. And the second thing is these are for the Excel that I forgot to send you. But we know that every of these nozzles are density dependent. Okay, let's go. Man, I forgot to give you all these Excels. But I go through it, and then let's we just go through the PowerPoint, and on lunchtime I give you the Excel and we can do it. Okay, so we have a different type of ICDs. The course is not about ICD. We just I talk about ICD, that we talk about wellbore, and then we talk about reservoir simulation. But then we do history matching on reservoir simulation, and then we do one example on pump, and then we do one example on geothermal, and then we do one small hydraulic fracturing. We just want to see different aspects of things, and the whole thing is about integration. So, and tomorrow I'm going to talk about integration. So that's the challenge on the petroleum industry that we have. There's one guy sitting just designing pumps without getting any background on what reservoir simulation does, on the geo model happens, what's the wellbore change. There's a guy sitting in service providers like Baker Hughes and Schlumberger designing these nozzles without having any of these things. And the problem is one part is software. We try to solve that portion, but one portion is organizations. There are a lot of these organizations, big companies, are very segregated. The production engineer never talked to reservoir engineer, reservoir engineer never talked to geologists, geologists never talked to geomodeler. So there's an organization segregation, but there is a software organization. Like this guy running Crossware, this guy running this ANSYS, this guy running this TNAV, like a reservoir. This guy is running control. If the software is one challenge, but the other challenge is organization also. So this is the problem of oil and gas future, I think. There's a lot of things that people get so much detail on, which is not as important because you're ignoring all these uncertain about you. So there's one version of these ICDs is helix or helical path. So you have this path going, and instead of having these small throat size, you have a long path, and friction happens. Friction happens, and you have this long path. The delta P happens through the friction of these long pipes. There's other ones is Baker Hughes belt. These stuff is they call it select. So there's a bunch of chambers. You come, yeah, a bunch of chambers. You come here, but it's more like friction. But they have these chambers. They have these vortexes. So this is like pressure loss coefficient versus Reynolds for one of these selects. And you see this shape. Is that reminds you of anything before looking at the next slide? What did that look like? It looks like a Moody chart. Yeah, you guys remember your Moody chart from your fluid mechanics course? So what is Moody chart? Moody chart give you roughness or friction factor as a function of roughness, okay? And so it's for pipes. That's for friction. That's for friction. So once you see some behavior like this comes down and go up like this, like goes down, up like this, that means your tool, whatever it is very frictional dependent. So it's follow the Moody chart. Just for your understanding how things are. So it comes down and go up exactly like a Moody chart. So that means it's a Moody chart. And there is a terminology in these ICDs. I just want to go through it because it's not an ICD course. It's a FRR, and that's a flow resistance thing. Once you have a less and less FRR, that means you got less friction, and that's this trying to tell you. So I don't have this example for you guys. I'm gonna send it in Excel. Example 2 and 3, I promised to send you in the lunchtime. So it's about, so in the first one, we do one simple example on Excel. And we just want to see, in that Excel, we try to get the nozzle size and everything there. And we just want to see what are the important factors. And here we just do the friction of this tool. And we just want to see what's the common equation for friction type ICDs. And we do it in Excel. And we want to see like how simple it is to make these tables using Excel, but that's not the right way of going to. Okay, let's forget these ones and then go to these. I still need like 4 more minutes to this CFD to be run. Some of you may have run it by now. Yeah, you guys done? Still running? Mine is very old machine, so probably yours is gonna be faster than mine. But you guys passed through the first initialization? You see it growth or no?
You can stop here.
Are you talking about the Excel data that you copied?
Yeah, you started?
No,
Some of you run it, like few of you run it, huh?
Copy from here and then.
Yeah, just do the create that Excel and copy it. I do it again for you guys. But I have to, let me just go through and show you how to do it. you create that Excel.
Yeah.
You did it?
Yeah.
Okay, go in the software. And come here, model, say add new city. And you come over here, go in the model, or go over here, application fluid. And then you have your Excel. You say copy, and you paste it. And you run.
Yeah.
Let me do it again for you guys. Nice meeting you, Dr. Andres. Nice to know you. I'm doing good. Thanks for coming. You have a laptop or anything, or just want to sit?
Just passing the interview because I will have to go very soon.
Oh, you have to teach a course or something? Okay, don't worry. Okay, where you go?
I need first to install now.
Go on the mouse.
It's new about
Then come here. And you probably paste it here. And what is it?
First I need to fix it.
Okay. I'll go there and. Okay. Come here, so. Let's leave it there. Yes. There you go. Yeah, so it's about this, it's about Eushaw Dynamics, which is the integrated software, and we're talking about the CFD portion of it right now.
Oh, I see.
Yeah. And then now we're talking about, yeah, so we just started. So everyone running now? Like 2 people, I help them like now. Just leave it there. Like it takes 7-8 minutes. 10 minutes. Because the software has to go and run it on different Reynolds.
Okay.
And CFD is time consuming. Okay. You have like 10,000 grids on those stuff, and you have to do all those matrix inverse. So one of the things also important once you get to the world of ICD and wellboard design, especially ICDs, and once you're dealing with different type of ICDs, is viscosity dependency on emulsion. Okay, so don't close the software. You can.
Still loading.
Yeah, that's initialization.
Yeah.
So initialization you have to let it go, because that's the important part on like everything you do, like reservoir simulation, like Eclipse, DNAV, like our software, and like ANSYS have an initialization. On initialization, software goes and do all these gradings, try to make it work. And the grading in CFD is not like grids in your reservoir, they're very shapy. So the CFD have to go and figure out what's the shape is the best. So that takes time. And then once it does the grading, then run. So don't close that one. You hit on your Eushaw software again and open it one more time. Please do it.
Didn't define the fluid.
Don't define the fluid. You don't need a fluid on that one. You run it or no?
Yeah, I'm right.
Yeah.
I just have to paste
You
it.
don't need a fluid on that one. Like forget the fluid. Like fluid is important once you want to see the charts. We only want to see the CV discharge coefficient of the function of Reynolds. And Reynolds is the dimension of this number. Fluid doesn't mean anything. Fluid is important once you want to calculate AD and connect it to the wellbore and those aspects, and you want to see the performance. Then you get important. Okay.
Yeah. I just
We only want to see discharge coefficient function of Reynolds. Fluid is not important. Fluid doesn't play anything there. It's not even in the formulation. Like, okay, mine's run actually. No, mine is run. You gotta see something like this. You run it? No, let's see run it. You just start. Okay, let's wait for everyone to run. Open the software and everything. Hit it again. And just go on something. Like just go on isothermal, for example, producer. And then come on fluids. Like something. Like just go on the emulsion.
Window model, right?
Just open it again. I don't want you guys do anything with that once just running the CFD. You don't want to destroy that one.
The window model, and after that.
Yeah. Go on new, go here, Blackboard mode. Yeah, just this one. Once you do that, you have a new one. I don't want to make a new one or anything. You just want to talk about this emulsion portion. So once we are in the world of emulsion, why is that important? Man. So who knows what's the inversion point is? No one? Never worked in the emulsion world? Never works on viscosity changes, disperse type of stuff? Okay, let me explain this and then we go, and this software we just explain it, and then we go, I think the next portion we go on the blackboard design, and the next one is reservoir simulation. So emulsion is quite important in any type of oil, all right? And emulsion happens in oil and gas once you got oil and water. That's the only parts we cares about. One of the most important parts happens on separators. Yeah, you have separators that you want to take the water out and you want to take your oil out. Yeah. How does separator work? One of these, you guys, you know,
Density separation.
density separation. And is that fast or slow?
It's slow.
That's slow.
Yeah,
Why is that slow?
because the fluid is flowing.
No, there are two. Like, what's the density difference between oil and water? If the API is 11,
0.
what's your density difference?
0.2 roughly.
What's that?
0.2 GCC.
Yeah, because
0.2
GCC.
especially gravity is 0.2.
no, I'm saying the difference because water is 1 usually.
Okay.
Oil is
That makes sense
0.8.
now. Yeah. Okay, let's see what's yeah. 0.2 is like API of
45.
45 is 1.2. Okay, so you're talking about condensate, nobody. You're talking about your shale oil stuff. Most of the oils are around 20, 25. Yeah. And the heavy oil stuff is 8, 6, sometimes smaller. So if you go API less than 10, that means you're heavy oil. Okay, so the separation happens because of density is small, but the biggest driver is dispersion of this stuff into the new thing, and that's emulsion. Okay, so emulsion doesn't let us separate. But emulsion is always important. This is the chart. That's the real field chart. Okay, and what is happening here?
From which view? This one.
This is Canada. This is not honestly. This is
Heavy oil.
15, API 15. Yeah. So you have a fraction here, and you got emulsion viscosity. Okay. And these endpoints of this graph is your actual centipoise of This is your oil viscosity. This is your water viscosity. Okay? So because it is hot, you have less than 1. But 1 is here, you have less than 1. Okay? So this is your viscosity of water, this is viscosity of fire. And you can have viscosity of what? 30. And that's the real number. Based on the fraction of what you got in. Okay?
Party of what?
Water fraction. That's the water fraction of the total.
Oh.
So it means like 1, everything is water, is your viscosity is what? This is 0 water fraction is oil. So I just want to show you how important it is. And that's real enough. Okay? So when is that important? Always, always, always. Once we're dealing with pumps, you are dealing with emulsion. Pumps break things. I'm talking about ESP pumps, not PCP or like plunger stuff. Like I'm talking about things that are okay. Okay. Once you have a high flow rates in your pipe, always you have emulsion. Once you're dealing with inflow control devices, always have emulsion. Why? Because it's a small nozzle, everything has to condense to go through it, and you break everything. So it's really important where you are at. And it's really important if you consider that in your model. Okay? So because the number are huge. Like you can be 30, but you are talking about 5. Okay, that's a huge difference on your delta P calculation and stuff. Okay. So and what is the inversion point? Let me explain that, and then we go into the software and just show you not only an example, but we just want to go more focused on reservoir and reservoir simulation, and then a bit of geothermal. That's a whole like one day on talking about everything. But really, inversion point in this case is 0.6. Inversion point is a point that the total fluid is changing its behavior on viscosity from being water dispersed to the oil dispersed. Okay, and it's a function of interfacial tension. It's a function of a lot of things. Really, what you have to do, you do the test and you get the number. Just don't trust the correlations. Okay, don't trust the correlations.
It means even the pressure levels will change at this point.
Oh yeah, it's huge. And I'll show you the nice thing about it is this is the real device in the loop, the tester. This is not the emulsion viscosity. This is delta P of these tools. They put it in these loops and they pass through it. And how is the friction and how the delta P looks like?
We have a huge pressure drop.
You see? You think you have this delta P, but you have this with the small water fractions. And the problem is what?
This one.
No, what is the emergent point? It's about 75. 7.6. That means what's your water cut? What is water ratio?
Water ratio? Yeah.
Water ratio, I just want to.
Talking about.
What is the water ratio? Okay, it's around 3.
Yeah.
Once you deal with water flood, you're always around that number. So you're always around that number. That's the problem. Like you're always around, unless you are dealing with the primary field, never been tapped in. How many of those exist? Maybe in Ghana there's still some, huh? Yeah, you're from Ghana?
No, from Cameroon.
Oh, you're from Cameroon, man. Like, yeah, you're different. But there are still some of those assets left, but there are maybe 0.5% of the assets left like that. You need it. There's not many primary reservoirs. Like everything nowadays, water flood, polymer flood. You do heavy oil steam injections. You have these shale oils. Now you ran up that. You have to do half and puff. You have to do some. Okay. In the conventional world, you're always around that inversion point. So that's a big factor. So you have to be care about it, understand it, and you take it into your modeling. So you see, you think about this, but you really are this, or you think about this, you are this. Okay, so that's a huge difference. So you put things in this. These are expensive too. Okay, so it's 100 million well, the offshore well, and you get extra 5-6 million of these costs. You put it there, and you see there is no delta V. So and say, man, and you can't. These rigs, workover rigs in offshore, they come in next year. You can ask them to be there. They go, and then you do all these things, and you think you do the best tools ever, and because you're missing some of these aspects, it's missing. So
I looked it up beside the design of the ECD, the
ICD, it's not just ICD in your pipes, in your pumps, in your a lot of things, but this part is ICD we're talking about.
because I just want to know how important is that.
These are important in your pipe flow and friction calculations. It's important. Is anything got viscosity term there, and you are in emulsion mode, this is important.
Excuse me, as you mentioned, that the cause of the emulsion is mainly due to the high flow rates. Specifically, we talk about the ESPs, which has like 60,000 gram per day capacity. So if we talk, I mean, in normal circumstances, we can control the choke size. We can convert from 24 to 36, 48, I mean, according to the reservoir pressure. So how we can control the flow rates and ESPs, I mean?
ESP, because you have a pump ESP, because you break in things,
Yeah.
no matter what your flow rate, you are emulsion.
Oh.
You always, like most of you. It's not a matter of flow rates. The part that say on flow rate is inside your pipe. If your flow rate is high, then you create this turbulence. If you have a water in this shale oil well, for sure you're an emulsion. Because flow is huge because you got this gas coming. Once you got gas, for sure. Yeah. Because rates goes orders of magnitude higher than what you're talking. But in flow control device, even if the rates if it's small, because the nozzle is wet. What you model? What's your throat size? The ones Excel you do, but I forgot your name. I will assume that. So just what's your throat size? From that Excel, tell me what's your throat size. You have to go and read the smallest number.
Smallest?
On the R.
1.75.
Onwards. Yeah. 1.75 is radius times it to 2 is what?
Is
3.5. Do you want to use a calculator? 3.5. 3.5 millimeters. Okay. And assume, what's your joint size? What's your joint size? How big is your joint?
How big?
The biggest one.
No, to joint, like the joints you put in a completion in your well. I just want to see if you have any idea. How big is your joint size? Give me in feet. You guys in feet, world?
Yeah.
4 feet.
4 feet?
I mean, again, what's the
No,
question?
the 30 feet. The 30 feet is a common number. Like, you have the smaller ones, but the numbers are 30 feet, like 10 meters.
The length of
The
pipe.
stuff you
Okay,
describe,
yeah,
okay.
okay.
And these things you supply them by June, okay?
Yeah.
Like, okay. So you have like 2 nozzles, 3 nozzles per joint. So you have like 10 meters, I'm a meter, is 5%, okay? 30 feet, I assume. And you've got 2 small size 3.5 millimeter. Whatever flow rate you have, one pass through there is a emulsion. That's what I'm trying to say. Like, it's 10 meter is like, this is like, maybe this is 5, another one, and you got 3 of these nozzles with this size, okay, in this offshore. Like, not many of those. And so you have to converge everything pass through it. And I'm saying the worst case scenario, you put it every joint. Normally you don't go every turn, you go like every 5 joules.
You put it through it or what?
Put these throats, like one of them is, and all of it is blank. Like, it's come like this, you buy the package and they come with a color. Like every joint comes with a color, like it's the red ones are blank, you screw them on, and you come with the green, let's say, okay, put 2 greens in your schedule, put 2 greens, and then let's put the red ones, huh? The guys on the redneck guys on the top, like the ones connecting everything. So that's how it works. Like I'm saying, there are not so many of those nozzles along the well. So for sure, everything converges through those is emulsion mode. Okay.
I didn't get the reason for such nozzles. It's like flow restrictions, what are them?
Why are you doing it? We do it run the software like one case and we see how that's important. Forget about these ones. And hopefully everyone have the CFD run now done.
Yeah.
Okay, let's go to CFD and we run one open hole model and then what was your name? Jorge? Hello?
Yeah, Aladdin.
Aladdin.
Oh.
Aladdin is easy. I remember that one. That's Aladdin. Aladdin without the genie.
Yeah.
I didn't read it. I think I got the result for the first one.
You didn't get it?
I got it.
Okay, everyone got it.
Yeah.
So this is the CFD. Okay, once we do CFD, on tomorrow I talk about it. About the whole oil and gas issues. This is scaling issues. We're talking about the scaling issues. But once we do CFD, we always talk about small things. Okay, forget about the wing of airplane. No one's small the wing of airplane nowadays. Everything in CFD, we're talking about small size.
The chalk.
And then I tell you the problem, and we talk about it tomorrow. What's your wellbore joint is like 30 pieces, and you put 10 of those and fill it. And then what's your reservoir grids in your simulation? 10 meter by 10 meter? Yeah. And then you put that, and then where is that CFD located? Like, is the scaling is huge issue. So then we talk about it tomorrow. But then, so this is CFD. We just talked about small nozzles and everything. So this is your CD. What is wrong with this? What is wrong with it and how to solve it? Okay. So this is Reynolds number. This is in log scale, always in log scale, because Reynolds is a dimension number. You have to be in log scale. You have to have a log scale mindset. If your Reynolds is twice bigger than mine, that's not important. Like it's 100 times bigger than mine, that's the times important. Okay. So this line here, that's that 4,000 I talked about it. Why 4,000? You can pick 3,000. But you have to have a reason for it. Like 4,000 is a common number. And you remember that Moody chart? Let's go to that Moody chart. And I tell you, a lot of these things comes from your fluid mechanics first or second year that you guys taught. Where's the Moody chart you talk? Yeah, I don't have it. But in the Moody chart, this part was, what was the friction on that one? Anyone remember it? 64 over what? No one. So we talked about the laminar flow here, and we talked about turbulent flow.
64 over Reynolds
In this one.
power 0.25.
That's a Church's law. Church's law is not for the rest of it. We're talking about Church's equation. This one is a straight 64 over Reynolds. And this here, this transition from this here, no one's had any equation for it. Everyone used something because it's hard to measure. Like that Churchill equation, like 0.25, is because we want to calculate something continuous. Software hates
Just continuity.
this guy. Yeah, Our software is all beautiful because you have to have a number. If you don't have a number, then in the iteration, like our software iterative. In one of iterative, you get to that zone, but really the final answer is not here. The final answer is not here. But the path to get to the solution, you may pass through here, and you have discontinuity. You never converge. Okay. So that's what I'm. Let's get back to the like 2,000, 4,000. So this is 2,000. This is 4,000. Some people say this is 1,800. But this is that 4,000 came from. It's not exactly the movie chart 4,000. It's something else 4,000. But I'm saying how people sure about these numbers? Not much. Exactly the same in CFD world. That's how in CFD also a bunch of equations. Huh? A bunch of equations like this one is one equation, this one is one equation. From this equation to that equation, you have to have that transition. So let's get back to software. And so we have this 4,000 line. And so the thing happens, come to this FCD coefficients. Okay. The software does, this is come from the CFD. Okay, so we calculate these FCD resistance factors based for every Reynolds. It goes and run it at 10, run it at, I don't know, 30, run it at this.
Okay.
And there's a fluctuation. Fluctuations like some fluctuation like this, some fluctuation like this. So this is the wrong answer. This is the wrong answer. Okay. Why is that wrong answer? It's very obvious that's the wrong answer. How to resolve it? Because we want to get rid of how many times it takes 10 minutes for us to run, okay? And we put 10 power minus 3. In CFD, no one put 10 power minus 3. But in our software, we put 10 power minus 3 because we know the completion engineers doesn't. They don't want to sit there like 8 minutes. So you don't want to sit there 1 hour. So we put this is wrong, but the right thing is 10 power minus 5. We put 10 power minus 5 and run it. Then you don't see this.
We continue.
We don't see this. Okay, so this means that part the software couldn't converge enough, and then it has some issue. And you see these fluctuations. If you do like 10 power minus space, okay. But the important is even if you do this and you have only 7 minutes sitting there instead of 40 minutes sitting there, and you have these dots, and this dots is that location. You see it dot. The software comes and curve feed all these points and use this in your bloodborne and reservoir simulation. So it's okay, like you don't have to sit there 40 minutes or 50 minutes or 1 hour, 2 hours. You can do it in 7 minutes, and instead of we honor these, and there is one gap between the data points at this location, and that's a transition because the formulation used for these, the formulation used for these are different. So to also pass that gap, and also for some of these points that are not converged completely, you smooth it with that curve and use that curve in your wellbore software, in your wellbore portion of the software. So software doesn't have to go this, and just honor this curve feeder line and get that, because we don't like discontinuities. Okay, so let's go on this part. Get error in the results. I come and see it. Like everyone's run it, other than him. Okay, sometimes.
Almost the vertical.
Is this a gaming software? A gaming laptop?
Yeah,
No,
he looks like someone.
Which one does it run? Yours?
No, you don't have the.
So, yeah, like, I tell you what happens. Like, that's a problem in, probably TNAV is like us, how to have that issue. Like, the software is make things parallel like us. We are really parallel. Like TNAV is also like that. So they give these like two different CPUs and these stuff, and they get it back, and they do this thing, and this is the new parallelization method set too. Some of the machines doesn't work like amazing with that. If you are running it with 10 powers minus 3 and doesn't work like that, do a 10 powers minus 5 and run it. It takes longer, but it works on your machine. So if you're using like gaming machines, like high GPU and stuff, with our softwares, I've seen that problem in some of our CFD things, and that's a problem. It's the problem is like the thing that the normal people doesn't know. The CPUs are not the same. CPUs are different. That's why you see Intel's now selling CPU AI. You heard that, like CPU AI, and they're quite expensive. CPU for game.
Yeah.
Those are different. But as a software, you treat everything the same. Right? Yeah, you have to do parallelization based on what you got. Okay, come here on CFD Venturis and go on 2D stuff, and you can roll the up thing and go like down up. This is your X velocity. Yeah, did you got it?
Oh, we are having some issue with it.
You got that one issue too. What? You guys see it? Yeah, just move the Reynolds like this tab. You did it. No, don't go arrow. Like go the where do you go? Simulation is over here. Yeah. Don't go to arrows and warning. Go on
Simulation window.
go on simulation so see
And
if
then
eventually.
field eventually.
Yeah.
We can zoom it more.
Yeah. You're in the wrong one. Like you are going just CFD. Which one you run? Just CFD. Run this for sure. Over.
Yeah.
And you have it. Why is it?
Simulation window.
So this first one is your CD. So you don't have that issue. And then you come to your CFD Venturi on your 2D. And you just scroll it. Yeah. This guy doesn't have it. He doesn't use the gaming machine. You're fine. Change this X velocity to R velocity. And these are the vortexes you see. You know the vortex?
Yeah.
So the more vortex you got,
Turbulence.
less CD or higher CD.
A higher pressure loss, so it should be
Less CD.
less.
More vortex, less CD. Yeah. So when that happens, the vortex happens once you have a huge difference. Like this end, that's a part that flow comes. The vortex normally flows around. And move the rail. Move the rail, they can't do it right now. And you don't see it here. You don't see the vortex here because the Venturi is designed to get things flow. You see, move the Reynolds, you see the location
Yeah,
of this is
they're
more.
changing.
Yeah,
Less pressure drop, right?
less pressure. Like the CD is a function of the pressure there, but also the function of how much you getting the delta feedback also. Okay, so also go on this one. And you move it. This red one is your velocity profile, and this is your dp. Move it to the end. And you see how the performance is. Okay, you come and your dp goes down and comes up. And this is your dp. So this is DP at throat. This is DP. Okay.
Oh, yeah.
If your PhD is on the shade oil stuff, for example, there's a lot of these discussions on perforation. Yeah. Okay.
So
That's exactly the
it's
same
like
thing.
pressure drop across the population.
Yeah. And the people just realize they have to do CFD, but this is because like I've seen it in HFTC, the few people does this. And actually the way they calculate this discharge coefficient was wrong. But the people in the FCD world, like they do that from the first day, like they do CFD on these for the last 20 years. Okay. So now don't close this. And
Does the X mean the length of the pipe or
what's that?
the X?
X is what you put it in your thing. Like that's the software comes and put the extra length ahead and extra length on the outside automatic. The reason is there is a length on the both side on the CFD that you have to put because you want to get to the normal flow. That's in software is very advanced, you have to do it yourself. But in this one, because we know the problem, we do it automatically for user. That's from the X of the software put it. That's good. I have to put the X based on the location. I revised that. Okay. And let's go on the black oil. That's the part you need to go and put your right fluids. But this is how your delta P looks like. If you put the right fluid properties. Okay. So save this. Save as in the desktop, I put example 1. And there's something in the PowerPoint I didn't talk about it. Let's do those stuff too. If you're really doing this stuff, for example, you want to show these vortexes, you can click right on this, come to chart setting, and see your vortexes looks like these colors. And okay, go on this, click right, chart setting. Chart setting, you did? You guys? What's that?
I'm asking him if he's recording.
Oh yeah, okay, recording, okay. Yeah, sure. So now, you guys run it? Okay. So click right chart setting here. No, save has to be very fast. It takes 50 seconds for the big reservoir softwares like models. Okay, okay, you do here. Okay, you hide all.
Green, it's blue for us.
No, just scroll down.
What is blue?
Just scroll down.
Oh, okay. Okay.
Different color.
Yeah, we are using the same software, man, the same version. Mine is probably one version ahead of you, but that has to be the same. Yeah, this blue. Okay, hide it all, and come and take these back, apply. So you got your FCD back, and then you want to just use these two. Like there is one negative and one positive. So whatever you're choosing, you choose both of those, like one positive, one negative. I choose one and I apply, and I get these vortex, for example. Okay, so these are the vortex here. And if you don't like the presentation of this software, what you can do is you say, okay, I click right here, show the data in Excel in the notepad.
To choosing that, you have to click on apply.
You apply.
Apply.
No.
Yeah. Like if you don't like, no, if you don't like, you can go to show data. This is not really important, but let's go. Copy these stuff in Excel. I just want to show you how. You just copy paste it. So this is the bottom part of FCD, the maturity. Let me do the top one too. So I get it back here because, like, let me see, 497. Put a gap here and then that's resolved. So now I just want to put that in my Excel. I don't like the presentation of this software, for example, or I want to do it analyzing somewhere else. And then those numbers of assigning it are giving you here. So you get this one, for example, and just do it here. Just want to show you like how you can do it. Yes. So I get this, okay. Yeah, so that's how you can get it. You also can export everything in Excel, but it gives you everything you got in that one. You can export it to TextPad, but the easiest thing is show data and just go get it what you want. In the PowerPoint example, we don't have time now. I did two different Venturis. One was this one that we did, and I did one longer. And in that one, we compared the pressure profiles. So red is the foreshortened one. You see the DP is dropping rapidly. This one is less drop. And we also compared the CDs. You see it's a different. And we also put these vortexes exactly the same way. And I did it in your in here. And I do it in Excel and we compare where the vortexes are at. Okay. So that's, you just want to see how the vortexes are different once you have the different FCDs. And the people are not crazy. There is a reason they have a differentiation. And the people like technology centers of these service providers, like Schlumberger, the algorithm, there are people like putting their time and like designing these better. There are teams of doing these. So forget the ICDs.
So why they are focusing on those small details if you have vortex on them? For example, in this case.
The more vortex is like you want to follow the flow regime as much as most as you can. Yeah, less vortex is better. In some of it, you want a vortex, like in select, you want more vortex, like because that's all relying vortex. Yeah, yeah, different ones. They normally do everything in the CFD, and then they go to the lab. And lab is expensive because one tool costs you about 400K to just do exactly what we did here. Yeah. So forget that RCP stuff. Now go keep this, keep that one, save it because I want to do something later on. You save this one. Example one. Example one. Let me have an example one here. Save it. I didn't save it. Let me save it myself. Example 1. Because we maybe want to use it. Okay. Now just go, just we follow exactly the same thing that we got. Okay. So now we want to create black oil producer. In this one, we're not linking it to a reservoir. We just want to use these FCDs with the wellbore and with the very simple reservoir models. And then we go dynamic type, okay? So go steps like that you follow in your PowerPoint. Just go and let me just go new project. And you come over here and you go isothermal. You just go black oil producer. And it's who run the console in his life? No one? The structure of the software is designed like a console, like a 3-base. Yeah.
The console is like for the 3D design, right?
No, that's AutoCAD.
There is console for 3D design.
Console is the software that linked to MATLAB that does the quantum physics and stuff. It does 3D, all the software that you need, but I think you're talking about AutoCAD.
For the fourth year, right?
Oh, okay. Yeah, people use it in first year. Yeah. Yeah. One of the applications. You can use this software for network. Like if someone to the PhD on this stuff, the core network portion of the software. Yeah, you do, but some of you use console. But so the structure like structure but like
Yeah, because for thermal application, yeah, we use console and for thermal application, material sterilization.
oh, okay, that's the show. Yeah, that's using console. But the whole time that saying the console, I just want to say that the structure looks like console. It's not as familiar with the 3 structure of the console. Most petroleum software is a tab base. You go out, come back. Console is like a 3-base. Okay, so go on the oil producer, and then we want to design our oil. So this is like Eclipse 100, like okay, have this mindset. So this part designed like a PVT sim, whoever run the PVT. So it's a bunch of equations. It's not compositional, it's not equation states. In conventional oil type, normally people work with this type of equations. So this is that part. If you want to do compositions, like shale oil, those are compositional based. So what I said in the PowerPoint, I said come to oil, and then go and use the API gravity of 29 and put the GOR of 640. Okay. Okay. So before you go on, in this software, you always can change your units.
Okay.
So you always can come over here and change your units. So if you have some of the stuff in field units, some of the stuff in SI unit, so you have to again go back to the. So now I give you GOR based on SCF over SCB.
Solution 640 or 750.
No, 650 is like a default number in the software. You put a 640. And then you go and use Lasso because so you read here on the bottom here. You read here, and it tells you that equation works better for what reservoir. Okay, so standing, for example, is come up with this equation based on California data. So that's why you cannot change this. Okay, so you go here. if you go with this is like more global sample, use a glass. Okay. And we can play with all of it. So that's we don't do it later on. We do it this time. Whatever is in PVTC, it's here. Okay. Now we want to have a composition of our gas, and we want to use that composition. We don't want to put this number here as just one given number. So we go in the gas, and we just use the composition. And then in your is 23194. Do I give you the right composition, or say 84 and 5? So use this one. Use this one 84 and use this 5. And you can test that by normalizing. So if you normalize it, it tells me, okay, that's not normal. So it normalizes it. So now we normalize it, is this one. So we go back to void, and we just say link gas. So once you link gas, you get that number.
160.
Don't type it. You just link gas.
062.
Yeah, yeah.
Yes.
What is the
84.
You have to have another one. Okay.
normalized? I'm done there.
Okay. Now, if you remember your undergrad stuff, once they teach you all these, what's the course name? Fluid properties, petroleum fluid properties, the McCain book.
Yeah.
Yeah, is that one? So if you remember those stuff, you can have all these correction and stuff. So now we have our composition. We can use the nitrogen composition. And you hit it on, you see your curve change. Yeah. What it does is change is your bubble point. Most of those corrections are above. You can consider all of the other ones, but nitrogen has the biggest impact. You can do all of them, but that doesn't matter. Okay. Now we come to the reservoir model. Now we come to the reservoir model. 50 and 1000. And check it. It says feet, so it's in feet. So if your software is not in feet, you have to go and convert it in feet. Okay. 50 well spacing task. So why is asking spacing? Because it's a single well. It doesn't have a dynamic reservoir in this section. So you just, this is more production mindset, completion mindset.
So what does it mean with the
So
location?
all of these wellbore softwares, like yeah, so they ask you what's the width of the reservoir. Some of them ask you the well spacing. So because there was a confusion and all those stuff, we use the well spacing name. But all of them, these models, like remember Joshi production course? No. So if you remember those courses, you take there's a productivity index formulations. And those are based on the width and those stuff. We use a well spacing. It's a bit, yeah. Okay,
How much do
1,000 we put. And some people like using different draw sheet, for example. You can change it to say 6 and you go to Josh. Okay. So
I think we didn't enter the gas composition. So I don't know why it didn't do that.
so go to gas composition. Go gas. This is like the simplest software ever. Like and okay. So recent went to somewhere like let me say it here also. Like if it's in a fluid, so we work with Saudi Aramco, for example. Okay, and Saudi Aramco people doesn't like to use any correlation, and they have enough money to have the PVT properties. So you can put these stuff here, but you have to come over here and say, I want to use their data. So for example, in this case, I want to use viscosity of 50, for example, say 10 and this 1,000. And I say 1, and I want to force it to 50. And I just want to use the viscosity. So the software take that table because Rickson was playing with it, let's just say, to show you guys. But for this example, we just go correlation, okay? So where I was on reservoir, we put 50 and 1,000. And this, don't wait for me, just go to the, go on the reservoir equilibrium, put your bottom TVD and you put your temperature, and that's in Fahrenheit. Just close this. Reservoir equilibrium, put this 120. You put the bottom TVD, what was the number? 6921. 6911. And now we have to put our trajectory, okay? Provide the trajectories, an example 4, there's Excel comes with it. So in Excel, I provide you the trajectory. Okay, there are 2 types of trajectory. If you're working with our software or Excel, Petrol and us are the same. You can put the Cartesian survey or you can put the deviation survey. Deviation survey, you have to use the inclination aspect. Okay, that's the standard Petrol standard. They go with the Petrol. Okay, so just get those. Just get these and copy paste it. Is Excel, there's Excel name example 14, come to trajectory.
So we go to the state or steady state?
Doesn't matter, use steady state. Doesn't matter. There are small differences. In ICD and production, of course, you test those, you compare it, and there are small differences. But this is like, we want to do everything of this software, but not everything in detail. So go on the producer and go on trajectory. And for this example, which is 1 well, it's not like a reservoir model, so you don't care where you put that well. So the wellhead is ignored in TVD, you just need a 0, okay? But once you want to do it combined with the reservoir, you have to put the actual number, okay? So now set pace. Once you copy paste those,
We don't have any support.
you don't have the example 14?
We have, but it's a PDF file, I think we copy the data.
We have from the PDF.
PDF.
We don't have the HFI.
No, there is a RAR file. Did you say that? Okay, I send it to everyone right now.
By the way, this license will go like for a couple of weeks, months, or
I'll give you 30 days. Normally in courses, we get 7 days. But for students, we extend it always. And we always, especially if the students work on the CFD world, we really like to work with them and incorporate their codings in our software and give them access. Or if they do something specific that works for us, we want to do that interaction. So now we do a lot of CO2 interaction, like on fluids and stuff, like we give them a full access on the other stuff, but then we help them to implement their code in our software. But you have to code it in C#. If you do C++, I convert it for you. But if you want to do Python, you have to learn the C# and you convert C++. But C++, it takes me 10 minutes to cover it. But, if you do Fortran or if you want to work with us, if it's really important for us, I convert the Python. But if it's something like not really important for us, you have to convert it to C#. So, okay, let me send you guys this example and we give a break. Give a break now until I give you guys this example. So I send you this example 7Z. But Jawad, I sent it to you and you sent it to her. But I think I sent it to you.
The PDF one.
No. I send you the link also. Let me see. Send. This one. Forward. Reply to Jawad. And there are 2 links on the bar. And I reply this. Can you just forward it to everyone?
Just forward it to
Oh, sorry. I'll put it on our website, the 7Z file, and you can just download it. I can do it again if you guys want. I can send you the 7Z, but some universities and some companies stop the RAR file, so I put it on a website and I give you a link to do it. Let me answer this guy. And then I get back to this. Nice meeting you, Mr. Andres. What's your family name?
Huh?
What's your family name?
Michael Mikhail.
Oh, that's your name, or Andres
That's
is
my
your...
last name.
Oh, Michael is your family name. Okay.
Yeah.
You are a Jesus conversion version of
Well,
Micah.
well, it's I think if there is EL in Jewish, it means
Oh,
God.
Mikhail.
So
You're Jewish.
no, I'm Greek. It's the same, I guess, conversion.
Oh, Mikhail. In Farsi, we say Mikhail.
Yeah.
But in Mikhail is like a different Mikhail. In Christianity, once Jesus died and converted into Michael as like an angel, us is the Michael or Mikhail is the once everyone's going to resurrect in the hell or heaven, he comes with the. That's a cultural thing. Mikhail is the ones with the horn.
Well, it's
He is Pakistani, he knows it. Yeah.
if it's a common one, if it's a common one, it means like
We have the same thing.
just.
You understand?
The same.
Yeah, but in Christianity, when Jesus resurrected and Michael is exactly Jesus, but in the version of the angel.
Okay.
And so, but in our culture, it's like the one with the horn, and like you guys. Looks like Africa, top of Africa, and Middle East, all of them talked about the same thing. What's they're talking about? Okay, nice
Well,
video. What do you
good to
teach
see.
here?
Well, drilling, completions.
Okay, that's a good
stimulation.
software. So we have
Yeah.
to, we give a full license to all the production process stuff.
Yeah, I would be interested in
Yeah.
for surface facilities to make I guess a master student project for
geothermal?
composition.
Oh,
in
composition,
surface
like
facilities,
aspects,
yeah.
like, yeah.
I
Yeah,
used to do that. I had a very basic code for that. Maybe.
no, like that part, um, yeah, so that ones I'm not teaching here. Probably Thomas will also join. Like, hi, Thomas. No, can I talk to you later? I'm teaching a course right now. Okay. Okay, sure. Thanks. I talk to you. So that part I'm not teaching today, but that's the part you're talking about. Like,
So you have a separate or registered filter?
oh, that parts we don't.
Yeah.
But for geothermal is the only place like we got like these stuff, but we can add it. Like that's not a big thing.
Mhm.
Like you put
Yeah,
like,
you have the components and
Yeah.
has the critical values inside.
yeah. These
So
are
yeah.
composition parts.
Oh,
We only do it
okay.
for CO2 and gas.
Yeah, I was talking about a very basic case that you can teach in a class. So basically, you use the Excel, the solver function in Excel, and you have a table for each separator or heater, any stage in the surface.
Oh, okay. Like
Yeah.
the refinery type.
Yeah.
Wow,
But
okay.
for, I guess, upstream,
Oh,
the
okay.
upstream segment. Yeah.
Yeah, like you tell us what we want and we can add it. Like
Mhm.
one function here.
Yep.
But like a composition part, you already tell name and software. We just have to see what you
Yeah,
looking
you
for
need to
and what
put
you
them,
add.
yeah, I mean, it's become more easier now that you can have everything processed in the same code, you know?
Yeah.
Yeah,
And we
very-
want to expand it. Like whoever helps us on expansion.
Yeah, I mean,
Do it,
eventually you will have it at some point, yeah.
No, but if you tell us what you want, we add it. It takes not much, like 2 weeks of my time.
Yep.
Yeah. But you tell me exactly what you want.
Very
Nice
to
meeting
meet
you, Matt. You got my email.
Yep. Thank you.
Okay, send it to link to everyone and then I send you, man. Javad, I send you, man. Like
I received the link, but it is not opening. I don't know.
you copy paste this, man.
Yeah.
You copy paste this
Then it goes to
Yeah.
energy then.
and you download it.
So,
What do you do,
Yeah,
man?
they are saying the straight
Okay,
with the-
like you guys do it in the here.
Mhm.
Like because I forwarded, you have to do it that way. Then you do it and then it comes.
Yeah.
It's on. I'll put it on our website, public
Listen,
domain that you guys can download. Yeah. It's fine.
Sorry, I have a question.
Yes, sir. Wellbore reservoir. It's integrated, like it has all the components, but does mostly wearable. But does the reservoir as well. We go through all of them.
Did you consider the transient or steady state?
For wellbore,
Yeah.
for the stuff we teach today, it's all steady state. In some cases, we have an option for transient model, like Olga, you mean? Yeah, we do. We don't teach it today, but we have it. Like in those cases, you want to open a valve or close the valve. If you don't tell that there is a transient model, but you say if you want to do it in 1 second, it's like exactly like Olga, that portion. Like you have to provide it, and for especially our software is like for like it's application for the problem. You give your problem, and it's more problem case. You say you want to open this valve, software goes for that part, run the transient. But if you want to run the software with the reservoir, it will run the steady state, you know?
Is there any advantage?
Against Olga?
Was it example for?
Advantage is this software is the only software like everything in one package, everything connected. You want to do the reservoir, you want to do well bore, geo model, and everything's quite integrated. And it's fast. That's the only thing. And it's easy. On some aspects like CFD, the other software doesn't have it. Like if you want to do like prop and transport, like a fracture, other software doesn't have a CFD. This has. But it's mostly inside the wellbore. There are some benefits that I'm going to talk about, which other software doesn't have. Like annual cost flow. Ever heard of it?
Yeah.
So we does the annual cost flow. The other softwares doesn't do it. The only Net2 does it. But we do it independently.
I think also depend on the flow rate.
No. Now that you're talking about multi-phase flow. Annual cost flow is like once you have multiple compartments and they're talking in this direction. All the software is this way. Whatever comes from the grids as reservoir comes into the node.
Okay.
Our software doesn't do that. It goes in that solve that whole compartment. And once you got the ICDs, for example, in flow control, that's quite important. This one get 10%, this one get 80%. The high perm area is here, but this guy here produces most, you know?
I think in order that software, the handle is using the nodal analysis.
That's inside the pipe.
Yes,
That's inside the pipe.
they segregates the flow, like nodal analysis, like Prosper now.
No, Prosper, those ones doesn't care about No. We talk about Prosper and those ones are, you provide the rate at the node, they give you depth of the at the end.
Okay.
Yeah. You can treat the software like that too. Like you say, I don't have any reservoir, I don't have anything. Just work with the rate constraint and just, we have example. We run one pump. But so this software is like Prosper, Action, PVT, Eclipse, and ANSYS for the CFD, everything in one package, everything talking automatic. And they're structured in the way that you can see all there.
Most times, there is a web is a complex system that can incorporate something like that.
Yeah.
Times, I'm thinking like the correlating types.
Yeah, we do all those. Yeah. We do everything that those guys does, but the thing is, like, if you do Prosper, you don't have a reservoir simulator. You don't have a right horizontal well, like software. You only have to care about the VFP model. So this software does everything in one package, and you see the reservoir effect. Some of the stuff we do, I don't want to talk bad about Prosper, but Prosper is very old. Like all the multi-phase flow in the Prosper is like 20 years old. Those are stuff we do way better. We do answer model.
Prosper did not consider the aspect of reservoir.
Example 4. Okay, recording in progress. So come and get your MD. Like forget this one.
Yeah.
Okay, guys, come here. You have your MD inclination in your trajectory. Just copy paste those. And make sure it's on deviation survey. Once we have a reservoir, we care about the wellhead location. For this problem, we don't care. Just put the deviation survey and just paste it. Just hit the paste. You should get this. And now we have to assign our MD for horizontal. And our MD is 8,355. So if you put it, you should get something like this. One portion of the well got to be blue. So that's what additional asked me. The gun is there. So that's what we do. Like the software comes and takes this blue part as a vertical section and try to link this as a different box on the horizontal section. So you put the 8,355. Now we're gonna go and assign our bottom of pressure. Okay. So we come and pressure profile cubing. You can do wellhead or you can do bottom. Okay. Now we do bottom hole. If you do wellhead, you have to model your vertical section. We don't want to do that. And what's the number? Is 2750. And you apply. Okay. And then you come over here and you assign your reservoir boundary condition. In some problems like the ones Al Hakim asked me. Your name is Al Hakim? Abdul Hakim. So in those problems, like here, you come on reservoir, come under reservoir. And on the boundary pressure, put like 3,000, put a constant. But for some reservoirs, if you do it in the longer time, you have to go and build it versus time versus this one, and you come and hit the pace. For us, we don't care now. We just want to put one number and run it. But you can do time dependent bottom hole pressure and time dependent reservoir.
How about simulating like pressure and flow rate at the same time?
Yeah, you can. It's a flow rate is also here. Like yeah, we have one example, but you can do it. Okay. But you can't honor both of them at the same time. You have to honor one and history match the other one. Okay. So then you go on your completion. Completion is on the producer. You come over here and you have to add your completion. Okay, so this software is really very detailed on completion. You can put the packer, you can put the leak inside your packer, you can model your flow behind the packer, you can put the gravel packs, you can put everything you want here. Like so, but here we just want to do it open hole. We just say concentric, and we come over here and say we want to do open hole. What's the size we put for open hole? What's that, sir?
Yeah, I was asking whether the software is
If you want to do it like a Prosper, you have to put the horizontal section like small, and then go on the vertical section and model. Yeah, but yeah, most of our clients are horizontal producers, so the important part for them is horizontal. But if you want to do it like Prosper, yeah, and compared to Prosper, they have everything. They have a better pump libraries and use some of the better pump equations, and we do way better heat transfer. Our biggest advantage is heat transfer. So go on the.
I still have a question that can you model the pressure and the flow rates at the same time? Can you tell us the possible?
Hassan Kabir equation for the multi-phase.
You ask the question.
It says you can model like a rate and the pressure for the software at the same time.
Yes.
I said the software you can provide both, but the software only honor one, and you have to discriminate the other one.
Okay.
So if you want to do rate constraint, or you have to do pressure constraint, one have to be honored.
Yeah.
The other one you discriminate. Yeah, that's exactly the same number.
But one is like given or
The software said your production constraint, you gotta do it. Like you said, like I'm gonna say, you said you want to do pressure constraint or you want to do rate constraint. So you want a rate, and you can provide both, but you have to do compare on the other one and see how good is your history. Yeah. The software doesn't do. Yeah, it does the automated history match here, but don't do it now. Like you can do automated history match. So now, but we have to put the right date. This software is like because it's not like Prosper. It's the time. It's like the software created to be connected to the reservoir dynamics, so you have to put the right time. So you have to put the date. Like because we want to do one point in time, then just leave it today. Today is April 13th. The software use that. Okay. Now we have to put horizontal permeability, water saturation, and all those stuff. Okay, that's a big difference. If you want to talk about a Prosper, those guys, yeah, those software doesn't care. Okay, because see it something like a fully integrated. So in the same Excel, I provide you all of those. So you have a pen, copy paste it, and you come and go under reservoir, and you go here and paste it. Yeah. Okay. Go on porosity.
So just like just click on paste.
Kilogram paste. Copy. You have to copy though. You have to copy. And in porosity and water saturation, make sure this one. If you are in fraction or percentage.
The middle one.
In here, I'm providing percentage. Okay. So some companies work with a fraction. You have to change this to fraction and then to paste. The software doesn't know like what's the unit that you're doing. So then to paste, and you do the same thing on water saturation. And water saturation is quite important because all your rel perm stuff works like that, huh? And you come over on water saturation and you paste. And then gas, you don't need it because it's above bubble point. If you below bubble point, then the software use the capillary pressure. Those we don't want to talk to, okay? It has its own system, and that's why some of these big companies really interested in the software because it solves the capillary pressure equilibrium. That's not other software does. But forget about that portion. Forget about fractures. Forget about all those aspects. And I think that's it. And we use okay. So you have a router, okay? So that's the biggest difference. Like sometimes you go to these well-born models like Prosper, they don't care. Like if you give them a rate, like this is not Prosper. This is full integration. All of them in one package. All of the things that the reservoir engineer and production engineer needed, all of them have to be inputted. You can't say, you can tweak the software in the way it does it, but we do it in the pump modeling, but this is not built for that. Okay, so now we go on RelPerm, for example. RelPerm is here. So we just use this as, okay, let's run this and eat pizza after. So.
It seems politically consider everything everyone on your own from experience, can you give us some any shortcomings you have identified about students that work on?
And not work on.
Yeah, any gap.
If there's any gap, tell us, we add it. Like that's what we said. Like now we got the one client.
Any gap for us?
Oh, and I tell you after. I mean, lunchtime. I said the projects that we are interested in people working on. Then we can put in our software and you put your name on it. So you can go on the LERPM and you can put the, I just love to teach you Honarpur because the people in the North and Canada are not familiar. Honarpur, you know, there's a book, LERPM Honarpur. You guys read it? No. The guy works at BHP Billiton, and like he has the best RelPerm book ever. And so we have all his book in his here. Okay. So
What's the name?
Honar book is famous for Honar book. There's only one author. But his correlation is like here. Like it's the only RelPerm correlation. You got lots of data on it. So you can use the rock type, you can use your stuff, and you put your perms, and you create your RelPerm. You see, that's the only. There is one software, GeoScout. I think you guys not using. You guys using AquaMap. What are you guys using for getting the data from the wells? Not because you guys probably not go to the industry. There are two main softwares that you can go and get your LAS files and productions for like your wells. There's AquaMap and there's a GeoScout. There are two versions. GeoScout has this inside of it, but for us we use Corey.
Yeah.
And come here and put 0. 0 means like prosper. 0 means you just want, you don't care about the time. You don't want to do any transit. You don't want to do anything. You just want a snapshot. And you just hit the start simulation and done.
What do you call it?
What's that?
Where exactly?
Here you put 0. It's automatic 0. For black hole, it's automatic 0. It's like the default is 0. You can put whatever you want and then hit the start simulation. Once you do a start simulation,
I mean the step before.
Step before, there was no step before. Like completion you did.
Yes.
Run the start simulation, see if you get the error or not. It says what? Get error.
Simulation complete already.
You're done. Like you got it. So now go on the result and then you get the like let's just let's finish this. Like at least we do something. We had so many issues today. So he says what? Oh, permeability, you haven't put it there. So go on your reservoir here, and I'll give you Excel. You have to copy paste perm porosity and what is that? You did it? You did it.
I need the water fluctuation.
You're on.
It's pretty last step.
No. Just go on Corey. Like, we don't care about it. Good, yeah. I just want to teach you the Honarpool because I know a lot of people are not familiar with Honarpool. But don't get like Honarpool is not a Corey. Honarpool is not a Corey. It has his RelPerm equation based on your pair, type of the formations, and 99% of the cases, you prefer oil and gas company, you don't have a SCAD data. This guy works.
Yes,
You don't have a SCAD data. But the geologists give you an estimate of the permeability. You know it's your limestone or sandstone. You know if it's water wet or it's mid wet or it's you know those stuff. So use Honarpool. That's what I'm just guessing.
Okay.
Corey is easy, but doesn't give you like you don't know what's your Corey exponent. What's your residual?
It's
Like
like history much.
Yeah, but Honarpool have all those. You give you residual water saturation. It has this. It has like about 40,000 data points to get those correlations. It's very massive. I'm not saying that's accurate, but it's better than that. Yeah, put porosity and water saturation.
Going forward, you can compromise. You might not have correct.
Yeah, like, but I'm saying most companies we don't have any more.
There is no
So,
scale.
like, yeah, normally you don't have it. Like, especially if you work for smaller companies, you don't have it. You have to go and steal like SCAD data from this Chevron well 200 kilometers away. It's for a different formation even, and you're using it. Like that's not the way. I'm saying like there is other way. I'm not advertising for Honarpool. I think you got it right. He doesn't care. But his equation is quite good. Like, and it's there. Like you don't have to. I know a lot of people create their Excel spreadsheets on Honarpool and they don't get the right answers. because it's a long book. It's like 200 pages, and you have to read everything and to figure out how do you do it.
More upgrade than query.
It's like a query, but it give you once you don't have anything and you can't do. It's like a custom, like in the rel perm. In the rel perm section, you can also go custom. A lot of people want to use this, but you should have it. I'm saying just use query, and for open hole, just start simulation. Hopefully everyone's get it. Mine takes less than 1 second. You guys, and once you run it, come over here on result horizontal section. You only see 1 point of rate. You only
For the lower completion, right?
yeah, lower completion. You don't have any cumulative. Everything is 0 because only 0 time. And so you can also make this 0 as 2 and run it again. And if you run it more than and then you see rates, but they are constant. You see the cumes, and you also see your completion on the bottom. So if you run it for 0, you don't see this picture here that shows your completion. A lot of people, like on the production guys, they care about PI. Once you get to the company where you talk to the production, and if you work as a reservoir engineer, the first thing they ask, what's my PI? What's my PI? So these are the things they're looking for. Like, if you work in US, you work with a barrel, and you don't have to do multiplication to get it to SI units. Once you run it, you don't need to go anywhere. You just come over here and you do a bar, for example. You go back to this. You go back to this, and you see everything now is meter cube per day per bar. Okay, so this software always can change your field. You can't put your permeability, or you can't put your pressure. If you give us in a bar, just convert it, copy paste it, get the barrels per day or meter cube. Anytime you can change the units. And these are the stuff you don't care. The people in North Sea cares about these reservoir stuff. Yeah, these are the oil coming, and these are the pressure at this case. Let me see if I finish this, then you can eat. But in the afternoon, we have to go faster, guys. Like, oh, let me do these parts also, and then you can eat. A lot of people in production doesn't care, but a lot of people. How many of you are resident? Everyone, huh? Yeah. The problem with the petroleum departments are, and that's not a problem. Like, if you want to do PhD, you're a reservoir engineer. Like this gentleman is drilling background, huh? For production. Yeah. Well, like, if you come out of Tulsa, maybe production background PhD, but 99% of the people, and that's caused a lot of issue in the communication in companies. So, and the geologist always, sometimes in bigger companies, controlling, and then they always have these questions from you. And so that's why we have it here. So then it comes to like this part. Go on the average grid properties. And these are your average grid properties, because the stuff you put was from the ASCII file from LAS files, but that's not software using. The software use the grid. Okay, so go in there and use the grading. And now, when we use, so now everyone's used the harmonic. And then you go on grid and you see you change your grid properties. Okay. When do you have to use harmonic? When do you have to use geometry? You tell me, Gregson. Our geometry is for permeability. layer type horizontal, okay? And harmonic is for what? Laser type, you do this, and geometry for everything. Yeah, like everything. Like so, normally if it's not carbonate, what do you use? Geometry. If you're using a sandstone, harmonic or like a. But the thing is, which one you have to use? Geologists and some of the reservoir engineers force the production engineer. This portion of the software is for production. They say, I don't believe you using average. And 99.9% of the software is using averaging. Huh? So we put this option for these guys, like
You can go with the average.
and yeah, you can do whatever average you want. And sometimes some people says, I have a fracture and I don't like the way you do it. I want to add the multiplier. So you say, okay, I add the multiplier. 77 to 790, and I put the marker at 20, and you see how it looks like. It's like this. Okay. Okay. I don't know what I put in the example, but I don't put anything.
What's that exactly for? The correction?
You want to correct that part. Sometimes they always say for that phase sheets, that correlation has to multiply. Sometimes they use it for fracture modeling. I know Saudi's using it for fracture modeling. We have a fracture, but they're still using that. So you can have the multiplier. Sometimes for history matching, some people doesn't play with the red perm. They just multiply. Because in the wellbore portion, you don't have a transmissibility multiplier. You only have multiplier for perm in the software. So then, I just want to show you the comparison also. So now we want to copy paste this case. Just copy, make a copy. Click right, make a copy, and name it as harmonic. I just want to show you how you do the comparison chart. The first one is arithmetic. And then go in the reservoir and go on here and delete this part. Just use arithmetic here and go on harmonic one. Come on the reservoir here, go and delete this one, and here keep the harmonic. Once you do it, then come here on the comparison chart, and then go back again to those reservoir readings. And click right on this one and say this is arithmetic. I have it in the PowerPoint also if you can't follow me. I'm doing it faster then. Come on the reservoir, come on here, and click right and say I want to do harmonic. And then you go on the comparison chart and click on this, and then you have a comparison.
So you save it?
You don't have to save it. And then you have to change your colors because you want to see it. Because this part I just trying to show you how to play with these charts. So this is nothing scientific. So you can, yeah, you can do the comparison chart, and then also you can, if you're interested, you can run both of them. Run this one again. And you create another arithmetic, and you can also change this one as flux. And you come over here and go on completion side and say this is my flux as arithmetic, and go on this one and go on result, and go on this one and say this one is Go group 2 and flux, and this is harmonic. And you want to see how the flux rate different. You come over here and apply, and then change the color. You hide all. You just say, I want to compare the oils, and say my oil and this one look red. And this is the difference you get on harmonic and geometric. It's just more playing with the charts in this example. You just want to, because you always need the comparison charts in your future life. This is oil rate. I did a comparison in this example. You can do exactly the same thing. And I'll show you how to do the multiplier. So this part, the user want to put the high perm zone here. You just use the multiplier with it and then run it. And okay, later, this example 5 is the pump. We do it later. Okay. So let's have your lunch, and then you have open it. Okay, you send me. Just open example 5. We're gonna test the pump here, and we want to see what we're doing here. We want to calculate the bottom hole pressure or wellhead pressure. Mazda Irani at ASHAW energy.com. .com. COM. Yeah, send me an example. So in this one, like we have the numbers in the bar, like SI. Let me see if I can get the side key for this back. What was your name, sir? Adeyemi.
Yeah, ADE.
No, I just put the license plate and
Okay.
names, so it really doesn't matter. Tennessee?
Thursday.
Thursday. Oh yeah, Thursday.
Thursday.
You sure you send it to me, man? Like I don't get it. Like, but okay. Open the example 5. Like till I get this email. Yeah, you make sure you get it. No, I haven't sent you yet. Like, why do I say thank you? Okay. Go in the field. Go in the change the units to SI bar. It's already in SI bar. Then come to your producer. Come your upper completion.
Black oil, the same. Black oil.
No, open example 5.
Yes.
Blackboard. Example 5. If you open example 5, the fluid, everything is there. The only thing you have to do is this part has to be on. Do you have to put it on? You have to say solve upper completion. Okay. And then you want to put solve upper completion, and then you want to go on your lift method, and you put, instead of natural flow, you put ESP. Let me check it and see if I get this. Man, I don't get your email. Like so go on the ESP and do breaker hubs. Go library TE 115. And number of stages is 25, already 25 for you guys.
But we don't have example 5. You can
In that RAR file,
you have the example on the PDF and on the Excel file. You
Man,
don't
I
have it
send
as
you-
a-
There isn't a example file as an Excel.
Yeah, as an Excel, but not.
no, not as Excel. Like you have to have an EDU,
There
like
is
this
you-
one.
Now open example file and go to nominate system.
Oh, okay.
It has to be like that. You don't have that.
You don't have this?
No.
I send you to Jawad and he send it to everyone. Let me get his code first. Let me send this to Jawad. Jawad, but I think I have it. Discard. Let me search your name. That's easy that way. And I think you don't have this one as well, the Excel. Send it to just send that one to everyone and open it and then follow the PowerPoint till I get site key for add the mail. I have to open this license. Okay. Jawad, you got it?
No, sorry.
Already send it to you. Oh, it's 23 megabytes. Let me go on example. You have a restriction on your files? Let me clear results. Make it smaller.
It's ED file, right?
EDU file, yeah.
I think it's in the RAR file.
Is it in a RAW file?
It's in the RAR file.
Okay. Okay, so
But the thing is, it doesn't open. It doesn't want to open. The license is simple.
you open it with the file. You open it with loaded. Loaded here.
Maybe
You did this, or you click on it.
I click on it.
Don't click on it, load it. Yeah, I suffered, cannot do that. Click on it. You have to load. You have to load file.
So it's not.
Copy paste it here. Paste, and then register license. And done. Okay. Done. You have a document. Yeah. Thanks for coming.
With the black or complex.
You open it up?
Yeah.
Go in the numerical settings, change it to SI bar. Come to producer, go on the producer, go on the upper completion. And you have to solve upper completion. You have to put a check mark here. If otherwise you don't do it, you don't get upper completion. For additional, which is not here, then you have option here. You can do mechanistics, you can do answering and asynchrony, you can have all these modification stuff. For now, we just use empirical. And the software doesn't give you a lot of empirical options because really trying to force mechanistic models. In black oil, use Hagen Brown. In gas, use another equation. For every type of fluid or a different model, use different type of empirical, but use the best empirical model for that aspect, but really want the user to go mechanistic. But the first run, always use empirical. So now go on the lift, UC lift. Previously was natural flow. Go on ESP, go on the Baker Hughes pump, and use TE1500 on the model and use 25 stage. And then pump doesn't work that way. You have to put the hertz already. And for the model I send you, you already have the hertz, but you can't put it apply. Put 60 here and hit apply. So pumps, we have an Excel example on the pump also after this, but we need to provide how fast the pump gonna work. So that's why it's time sensitive. You just put 60 and it goes for everything, but you have to really put for every time the table and you just paste it. For our case, we just want to do one. And then go on the configuration. Go on main tubing. And on main tubing, you have to put a size and you say you want to start MD0, but you want to end at 2952.76. 2952.76. And click somewhere and it goes to the end. You can have it shorter if you want, whatever you want, like 2850. Whatever you want, put 2900. Whatever number is there, put it. And you put the OD ID size of the tubing. So it's 5.55. You put a roughness, whatever you want. What do you have to do now? You have to put the rates here, your production rates here. So I think I have you the production. You have example 5? You have example 5? Okay, so I have you example 5. So you have to put these rates in that section. So you put the fluid rate because these are the rates that you want to honor. So you have a shutting, you just write shutting the places you want. Come on the fluid rates here and just say paste. I don't know why it's not working. Let me see. Put the water rate. Water works. Let's put the oil on the oil. Copy. So it doesn't work. So because it doesn't work because I put a shutting. So go here and put a shutting as 0. See if you have any shutting. So you have shuttings here. So in the shuttings, you have to put 0. And then you copy paste. Oh, why is it not working? Oh, oil work. Fine. You put a paste and okay. So now I have water production and oil production. And what else? So we put a tubing, and we put this. On now we have to go and put the production constraint here. So instead of pressure control, we want to put as rate control. And the rates are honored as a field production rate. So you put a field oil and if with a field water. What software does honors the liquid rate. That means honor the combination of oil and water. So whatever you put as oil and whatever you put as a water, it honors it. And in simulation setting, then you come and you say, I want to run every simulation. I want to run every of the points of the data I have. And you have to put this one. If you put it like numbers here, then you go and segment it and interpolate those times. But we want to honor all the data that we have. And at the end, we just run.
So in this case, the ESP pump is already designed. We do have it designed. Can your tool allow us to?
So the way people does it, like you go and so this is not for design. This part is not for design. It's for like the user want to put want to see what the wellhead is. Like already put it. Like you know the rates. Somehow you want to honor one of those. For design, normally is like there are the steps, and I go through it. I go through the fast design aspect. Let's finish this and I go through it. And I tell you how you design the ESP. There are three things you have to design an ESP. Mainly you have to do it like, and I'll tell you how to. But this example is not for design. It's once you put an ESP and you decide about it, and then you want to see what's your wellhead is.
Yeah, I used to do the design with Prosper. So first thing is like once you specify the target flow rate and the outlet pressure, from there it can give you an estimation of the power horse needed. You select the motor, and from there you go to the stages and the components.
Yeah, sort of, but yeah, let me just yeah. The first thing you have to design is if your ESP is capable for that rate or not. You have your rates.
Yes.
And then you have a sizing of your casing. So that shows a limitation. Let me go through those, and then at the end, you want to see if you can get it to the surface. If you get it to surface, with what pressure you get it to surface. So this is the last one. We want to see what's the wellhead pressure is. Like if it's give you 100 bar, and if you give it 100 kPa or 1 bar, that means you don't get to the surface. That's how this works. So now we honor the rate. So we treat this like a prospect. This is how we treat it. Because we say, I don't care about the horizontal section. I want to honor the rate. But there is a problem in this way. If you put your perms pretty small, your horizontal section, you have to give it very high perm in this type of thing, task you want to do. If you give it like a very small perm, the software cannot get those rates. Try to get it, but cannot get you. You don't honor your rates.
Your rates
give
you like
so think about it. It's not Prosper. You can't treat it like Prosper, but you have to put a permeability good enough in the horizontal section that software can give you those rates. Yeah, Prosper doesn't care about horizontal section. It doesn't care about permeability. Like,
yeah, as long as you give him like the IPR.
Yeah, it just yeah. So you have to give it enough rate. So if you come on the horizontal section on the lower completion, yeah, and the Prosper and those ones is one node in life. So these dots are actual field data, and the black dot is what your software did, what's matching. Okay. Yeah. So normally, if you are a reservoir engineer and your manager doesn't know about anything about reservoir simulation, and you want to give him the best history match ever, you're honoring rate. I know some people does, but that doesn't give you anything on a reservoir simulation. You can't do that. Like you have to give the bottom of pressure and match the rate. But a lot of people does. But in this task, the task is different. We want to treat this like a prospect, but we want to treat it like prospect. So we honor the rate. We want to honor these rates, and we want to see. So this is the actual. This is a true example. In this example, we didn't want to design the ESP. We know the ESP, But the user, the company that provided us the data didn't provide us the bottom hole pressure. They provide us the wellhead pressure. But in the software, to get the faster answer, you have to put the bottom hole pressure as a simulation. So that's how we calculate the bottom hole pressure, and then we put the bottom hole pressure for reservoir simulation. So the dots are what's the field are, and the black is simulated one. And you see after this one, there is no dots, and he just honors something like a bottom hole pressure or something like this. And so this is the drop down of the horizontal section, but the Prosper is on where? Prosper is on upper completion.
So this is the pressure curve for known flow rate.
All right, so this sucker has a horizontal section, upper completion. Okay, so if you have the horizontal section, we don't care here. Like in this one, we don't care. Like horizontal section, we just put it, but software has to solve. You know, software has to solve horizontal section to get to the upper completion. Yeah. So you always have lower completion in this software. You can't ignore it. So this is the bottom of pressure, and this is the wellhead pressure. So you calculate the difference. And then you also can go.
So the difference is calculated by subtracting the hydrostatic pressure?
No, you calculate it. This is the height. So this is the node. Here comes the flow. This is the pump. And this calculated based on is a combination of hydrostatic and frictional. If you change the tubing size, the answers are different. And you do it versus time. Like if you have it here, you change the time. Yeah. Look at this part. This part, you give the time. You scroll it back and forth. The thing here, you have some temperature.
So in a way, it's like Olga in this case give you like some transient results, not that fancy, I would say. There is no specific outcomes regarding the
Olga is a transient mode. This is still a steady
steady state.
If you want to do transient, I'm not teaching it today. You can't do the transient.
Okay.
But transient is normally where stuff happens in very small timing, like 2
Couple
seconds.
of hours.
No, couple of hours. Everything is steady. Like 1 minute, 2 minutes. Like if you 1 hour, you want to change everything every minute, then that's transient. But if you keep everything constant, additional is here, not here, but he provided me this TI formulation for time-dependent transient. But the transient that Olga does is a pipe. That is for a very small second. If you look at the one we do, we give every multi-second, like millisecond, what happened. Those calculation is for those. They model the shock wave. Yeah. And the formulation they teach you in like you can do without loop, like a multi-phase flow. Those are not built for transient. Those are, but you can do it in this software. But in this software, it doesn't tell you the transient. It has a choke. You want to close a choke, and you want to open a choke, and say how long it takes, and then it runs for you for that time. And normally goes 20 times after the period of 20 to 30 times the period of it's doing things like opening or closing. If you go to academics, all the papers they publish is about closing the okay, so this is the pump. Pump is just the formulation, we're going to go through it. And this is the DP, and we have a time, delta T. I'm not sure if the Prosper calculated that temperature, but there is a delta T happens due to energy loss at the pump, and that goes into the fluid. Because heat transfer is turned on here, you don't see the change, but you see that delta T coming. Okay. You also can see corrosion. Corrosion is important. So in this example, we have to do the corrosion study. So what I show in corrosion, this is not the corrosion. Oh yeah, that's it. So in corrosion, what is important? The water chemical is important, chemistry. So you put your water chemistry. You have to put your water chemistry, especially the H2S and alkalinity. And they have two sort of corrosion modeling. One is the pitting and one is general corrosion. What is general corrosion? That means normally general corrosion never happens. That means like all of the pipe degraded this much. Pitting is like you have a small hole and that's corroded. Like that's normally happens. So you can go here and see the corrosion and stuff. I have to wait because you have to populate all those data. So it gives you water solid accumulation, those stuff. It is really important for corrosion. Now we come to pump. Come to ESP pump. And once we come to ESP pump, then we see the power loss, efficiency of the pump. And we also see these charts. These are the stuff that Prosper does, like for example. So we're going to talk about everything. So flow rate head. This is the charts. We have example on Excel and we're going to do it. And this is what we can get. But really for head and efficiency, it's a function of the rate and viscosity. These charts that we have it is for viscosity of 1. We have to convert it to viscosity something, and Prosper does it. We does it too. So you have a new formulation. So you can use the Schlager, for example, like efficiency chart and those stuff. You have to convert it. So ESP is there for some people like to use these corrected performance curves. And so the steps in designing the ESP that your buddy asked, normally you have to go to selection chart. So normally you buy it from one vendor. So you don't go Schlumberger and then go Baker to some other. You always buy from. Okay. And that vendor has list of the pumps. And you know your flow rate. You know your flow rate. And normally the number here
reflects the range of the flow rate.
Yeah, that optimum. So that 1500 is the rate number. It's sometimes in barrel a day. For some companies, it's meter cube per day. But you always have to put it in performance flow rate versus head and see where you are. And you normally take a look at your rate and say my rate is, for example, 1200. And on this here, it gives you the flow rate number. Now it's just in the bottom here. It's give you flow rate number and the head number. Sequence. And you go there and you say, okay, this is my flow rate number. And okay, so you don't want this thing turning. So you say, okay, this is not the one. I want to go with this one, maybe higher, but the delta P range is a smaller. So I have to go bigger one. And you do this here. And also the other thing is casing size. You have to be able to fit your ESP inside the hole. So that's the other limitation. Once you do those, then you use Prosper or this software or whatever, run the simulation, and you see if we can get the
rates
to the surface. And sometimes you have a constraint on the surface, and you don't want the bottom hole pressure be at something. Okay, so then that's the case you do, and then. Now we want to trick the software. You know what we did? Without simulation, we changed the pump. So the software doesn't do the simulation, just only come and change this part. And then, but finally, we have to do simulation because it's not very accurate. But you see, this is the smaller now. So you can do those and see, okay, what roughly I'm getting. But at the final time, you have to run it because these things coupled. But for short calculation, oh, you get it, but this is not enough. This is not enough. You want it at least 500 bar, for example. So you run it with higher number of a stage, or you change your pump. The higher number of a stage, the stages is a multiplication to your delta P. So if your delta P of pump is 100, you times it to 25, 2500. Okay. So now we did this. Now we want to do Excel example to understand the pump. We want to create these charts. So if you know what's the affinity law is? Affinity law? No, never. Okay. That's how the ESPs work. So open example 6, that's Excel. You guys like me just run the software or just want me to go back and forth Excel? And...
Let's see what.
Yeah, okay. Oh, yeah, okay. So run the Excel. So this Excel is, I'm trying to create this type of radar, this budget, for example. Like we just want to see what is the ESP looks like, how we can do, because Prosper and some of these softwares give you the capability to load your pump. And I just want to tell you what's the background is, what this software does. Us does the same thing.
PipeSim does the same thing.
Huh?
PipeSim
doesn't know. Yeah. PipeSim and us got better library. Prosper got less. Library, it's just a matter of time to find one student to go and convert all these pumps to something. Yeah. Prosper doesn't do it. PipeSim and us did that task. All of them do the same. Like all of us do the same, but maybe the correlation inside of it is one is order of 5, one is order of 6, or whatever. You can see what's the difference. Okay, so we have. Don't save. Okay, so. So we have this flow curve, like, so normally people go and digitize these stuff, or they provide you these numbers in the Excel or whatever. So this is your pump curve. And now we want to see, yeah, we want to change it on different RPMs because what's these heads and efficiency that these are provided, you can see on the top it says what? At 50 hertz. Yeah. Some of it at 60 hertz, but you're running at 30 hertz. No one's running at 60 hertz. Like you normally don't run at high end. You always run at 30, 40, those hertz. But these charts are either at 50 or 6. Okay. So now what we want to do is we want to curve it. My computer give me a hard time now. Don't. No. Okay. So now this is our formula. Now we want to curve it to the formula, a quadratic formula, which has C0, C1, and C2. You can go to C5. You can do whatever. The more you go polynomial is the better. But so this is just teaching you how to curve it and how to put the affinity law. Looks like not many of you are familiar with that. So who used line set equation in Excel by now? None of you? So once you got the multiple variable, that's what you do Excel. So copy paste this line set formula and put it in G21. Put it in G21, which I already put it for you guys. And what you want to do really is you want to curve fit these data with the order of magnitude of 2, but you also want to include x in it. So if you want to do x3, you just put this x power of 3, you just put it. Okay. So this equation tells you you have alpha plus Vx plus C times x2, and really calculate you all of this. So you come over this, and once you get it, you have to get these, because it's a matrix of 3 by 3, and you say Control Shift Enter. Am I right? Control Shift Enter. So you go here, Control Shift Enter. Okay. No. Control Shift Enter. Yeah. Oh, I'm holding the auto. You guys got it or not me? Just not me. Control Shift Enter. Shut off. Okay, let's see how this works. Control Shift. Okay, you guys work for you guys or just not me? It doesn't work on my machine. Is it working? Okay, it works for you guys. That's good then. So then we want to convert that correlation to have this. It works or no? It works for you guys or no? Oh, what I got is Mazda. So it has to convert it to. Okay, let me just get this. Let me just get it. Control C. Let me delete this. And then put it here. And enter. Control Shift Enter. Okay, it works now. Okay, so delete that $sign and just get it here. And then put it here. And just do this and Control Shift Enter. And it works now. Do you guys work or not? Let me see. You're not Excel. Who has Excel? Just delete that first part. No, that alpha. Deleted. And Control Shift. Oh, it works. Control Shift. Okay, now it works. So you have to get not applicable on the end side.
Yeah.
And so now you've got the parameters that you want for the curve fitting. Its line set is quite helpful, like once you do experimental studies. So this is your R square. Always, this is your R square on the corner side. So C naught is, I think it is this one. C1 is the one in the middle, and C2 is this one. Let's have a curve fit it now. We want to curve fit this D10 on D10. And we want to see if we put it right. No, we didn't put it right. So this is this, and this is this. You see how accurate it is? You did it? Oh no. You gotta see it exactly on those. Very good. Okay, so this is this. This. Yeah. Just drag it.
And C1 is,
The one in the middle. Just drag it and you get off.
so it's all the first line?
All of it. And then put that quadratic equation that links to that C, not C1, C2.
And I have to basically one column?
Oh, yeah. You just wanna, you know what we're doing? Like, we
I
wanna,
got it, yeah.
we have a head versus flow. We just wanna currently this head versus flow and have this new. Okay, you got it. Okay. So now you got head versus flow. So now you have a quadratic formula. This is all this software does. So they curve fit the polynomial equation. And now here it shows you, if you look at here, on the here, see that in the way it tells you what's the formula for your head. You guys got it? No.
Go to the C, it's you are this, but how do you get care?
Oh, that's quadratic in the PowerPoint. Go in the PowerPoint. Okay. Like the PDF you have. The next one. Oh, not very. Have to go this way. Go. Yeah. Okay. So this is the one. Copy this is the question. And put it in D10 and scroll it down. This video. No problem. In the head. Okay. Or just put it in here. Yeah. And just scroll it to the down. Drag it. Okay. This is here. Oh, we put 14. This one is this one. You know? That one is this one. Okay. No, easier than that. Just put this one and drag it. Just go here and say this one is this one. And just drag that. Drag this to get drag C0 like that. I can't work with yours. But just drag this to again. Yeah. No, well. Keep it over. Okay. So once you got the experimental data,
Thank you so much.
Yeah, see you, man. Once you got experimental data, this is a very good way of curve fitting. If you need like higher orders, you can just put comma 3, comma 4 in your line set function. Okay. So now you learn how to curve fit it. So now we have a formula here that fits this stuff. And this is R squared. This number here is R squared, 0.99998. Okay, now you have to create it for for 60 RPM, you want to do it for 45 RPM.
So the red points are the lights, right?
The red points are the digitized values you got from the chart. You now curve fit it because you need a formula to use affinity chart. Affinity formulas. Otherwise, you cannot. Okay. So these are affinity formulas. Okay. The rate is linear to RPM. The head is relevant to the power 2 of the RPM ratios. And the BHP, which is power, is power 3. Okay. Oh, you're gone. Oh, today is not the spring break? I thought it said spring break. Okay, you guys go.
For like 2 weeks ago.
Yeah, it was 2 weeks ago.
Oh, okay. I thought I came on the spring break. You guys. All right.
Snow break.
Snow break.
Snowstorm.
Oh, okay. So now you got affinity chart. And now what we want to do is what? We want to use these stuff to get to our RPM. We want to do it for 45 RPM. So just do it based on this. Like what I said, the flow is just the ratio. The head is the power 2. We don't do this one. They don't do the power. We just do the head and the rate. So rate is the first one. Just go on the P9. P9, where is P9? Is this one, and just do this. And just do this on the head modifier. So these are multiplied to your whatever you have. And then do this. Now you have to use the new formula. So you can't use that polynomial. You have to use the equation based on these modifiers. So it goes on A2. This one's go on A1. And this one goes on A0. So, did I do it correctly? This is P10. Put everything.
We have also people for 18, 17, 16.
You guys write it right? I got it wrong, huh? A2 is P18. Oh, you know what? I put it wrong way. I put P18. Yeah, I'm doing it other way around.
So there is something wrong in this slide here. We have O18 is A2, but in the Excel, A2 is.
Oh, okay. Let me just make sure. Like, maybe I just put it upside down. Let me put these both as 60 and has to go above the chart. Okay, this is 60 and I put like 45 RPM. Yeah, this is what. And there's no curve, new curve coming. Oh, I have to create the new curve here. Let me create the new curve and then we see what's we're doing it right or wrong. You have to create the new curve here. Okay, so this is this. Let me just, I'm not sure if I'm doing it right here. No, that was right. Like previously was right. So so A2 is, so this is A0, this is A2. And you say this is 016. Let me fix this for you guys.
13, 14, 15.
Yeah, 14, 15, 16.
14, 15.
Yeah, A0 is the bottom,
Yeah.
16. Okay, I do this 16, do this 16, do this 7, 15, and do this 14. Okay, guys, I fix it now. In the last conference, I fixed it, but I used it. So now you get the, you want to see what's your flow rate at 10 meter cube. Your head is modified version is 13.98, but your if you go based on 60 RPM is 1267. Yeah. So if you get the 60 RPM over 60, then you get it. If you have a 10, you see you get a very flat line. So it's 40. So now the people like in these softwares, how they use the RPM. Yeah, that's how they do it. Us is the same, everyone. But no one's used the quadratic. They use the order of 5, order of 6. We use order of 6 for efficiency. For other ones, we use power of 5. The problem is once you open the software, if you open the software and
You get the curve.
you then get the curve. Oh, the curve, you have to put this equation on E10 on here and here, the new head. That part you have to do. And let me get the Blackboard producer, and then I can do the pumps. I want to show you something, and then I say why that power sometimes doesn't work. Let me see. You want to get what funny shit. Okay. Some of these pumps have these shapes. So you cannot work with power rack. You need power 5, power 6. So that's most software goes as standard. You can't say for this pump I use power rack. So you go with the higher orders and then use that through your software or whatever.
So this is flow rate and pressure, right?
This is head versus pressure. Yeah, flow rate and efficiency is here. Efficiency, the green one. And you know what, guys? In that thing, I didn't teach you the pump location. I think we put it, already put it in the bottom. But you also have, let me just teach you guys this one as well. It was a pump 5. So you have to put the pump location as well. Okay. But in that one, I think the pump location was built here, but you can't change it here. You can put it 900 or whatever. Put it like something that you see the change. You can't put it the location, okay? In the pump location.
If you go to the efficiency curve, what about the growth graph?
What?
Or growth graph from efficiency? Yeah.
These two?
Yeah.
This is not relevant, man. This is this axis, this one is this axis, but the Y's are not really relevant. Yeah, that there's nothing about this. The only important part is this range between these reds on the range of operation, and the green one is the optimum operation. But yeah, forget it. Like forget those stuff. Like if you want to do the detail pump design, you have to understand it. So I'm not going modeling questions, and I do it later on. Let's do one reservoir simulation, history matching and reservoir simulation, and build a geomodel and those stuff. And then we come to inflow modeling and annual cost flow and those stuff. Go on, open example 10. And you don't have example 10? Or you don't have example 10. So you just, the new model, you have it? As Excel? No, you don't have it. Just say new.
You have an EDS file. You have the EDS file, for example.
So you have a file? Why you can't load it then? You guys can load it then?
It's in the raw file.
No, you have Excel. You don't have an EDS file.
I have the EDS file. Example 10. Yeah, it's in the folder.
Oh yeah, you do?
Yeah, it's in the folder.
Open it and see how it looks like. You see the multilateral thing? Is that for the people who doesn't have it? Like, I think this one.
There is dynamic water plot. Dynamic water plot.
Oh, so you have it. Like other people doesn't have it. So let's load. Forget it. Like, assume you don't have it. Come over here and say dynamic water flood. Open it. And then go in the oil. And put the properties, as I said, 15, 50. And this is, they call it unconventional. They call it conventional heavy oil. This is actual well in Canada. Yeah, 50, put it down. But this is meter per meter, like make sure you put in meter. So this is SCF per SCV, okay? So what you should do, you should come over here and put it, the field, and go back here and put this 50. Okay, you guys got it? You guys got this part? It has to be SCF per SCV. GR, not meter cube per meter cube. And what rest? You put here 60. You have to have your separator design. Separator only used for like is only used once for your final oil rates and stuff that matters. Doesn't matter anymore.
You have to change the version.
14 point, yeah. Put 14 point. You put the separator's number there, and you use a standing. And what do you use? Use Galasso for the dead oil, and use Chu and Connelly for expert for the life saturated. Okay. And what else we want to do? We want to honor the viscosity. So we come over here, say 100, and we give very large number on PSI. And it doesn't matter what we put for BO, but the important part is this viscosity, because we want to honor this. That's the number comes from the client. That's you have to honor. So we say 1456.4. RS really doesn't matter anymore because you don't really want to honor that one. Yeah, so that client wants you to force the viscosity at one number. Okay, so you put one low number and one big number. So you see your charts didn't change yet. So Glasso standing, dead oil Glasso, life saturated is Chu Connelly. And the nice thing is here is your viscosity. Okay, your viscosity you see is like 50 centipoise. but the user wants you to put this number. Okay, so the models cannot honor that viscosity. So you come over here and you have to say in here, import experimental data, you have to say user defined data. If you put correlation, it goes back to this. You want to honor this. Okay. You did?
I think it's different.
You did that 14, like come over here and use this one, viscosity, user data. So you want to only use viscosity from the table. You did that?
Yeah.
Everyone did this? Okay. So now what do you have to do? So now is the task begins. This is the real case, multilateral well, and we want to do everything on this. So our reservoir is at 800, and we want to honor the pressure at 568. So we come at reservoir, and we go at reservoir equilibrium. But look, here is a meter, it's not feet. So now we have to go back and change our setting to KPA and come back to model. Okay, so now we say 800. You guys got it? It's already 100, 800?
KPA.
Yours is KPA? So what do you put viscosity in oil? It has to be 1.4564 if that's Pascal second.
Yeah, 1456.4 Pascal second.
So what do you put? You put 1.4?
Before. No, it's more. It's
Oh, okay. You opened the example 10 that you had it and we don't have it. Okay. So these guys don't have it like me. I thought I made a mistake and sent it the solution. Okay. So that's the part I'm saying. Like, don't confuse. This is Pascal second. If you use a field unit, it goes to centipoise. So now come to reservoir model and put this TVD at 800. And put the pressure as 5,687. Yeah, 49. Yeah, do 490. Okay, that's all. And then now you have to go, you have to add the well now. So done. This part is done. We go on the well. You guys doing it? You guys, you're doing it? Okay, go on the well and you have it here. Add new, you see me? You go on the well, there is an add new phone, add new well, and you say producer. And change that producer name to, we have 8 branches. And in the Excel, you already have the wells, huh? Al-Hakim?
yeah, I have all the work. Now I have to.
So that's a solution, man. Like you're using the solution. So,
But I'm adding
yeah,
producer.
you have 10 wells already and you add 1?
Just to follow.
Okay, to just follow. Okay. So you just do 1 then. Just get this name in the Excel. In the Excel, you have a trajectory. And come and rename this to this. So this is the well name. And I think you guys works with the township and range here also. UWID, you guys, or no? You know what's a UWID? Unified Well ID? No? Okay. I bet North Dakota is the same. You guys have a township and range. On the way I came, like it was, I saw ranges and townships. What is township and range?
like line and column, right?
Township and range. Range are these ways. Townships are this ways. And like a space, like in a space, like in the XY.
For the word, I don't do neighborhood in
Yeah, you know, like,
condition, yeah, it's
yeah,
it's the street and avenue for the word.
the streets and having. Actually, they created for farms. That's the first time in North America, like US and Canada, you came as immigrants from UK, that's how they get the land. You say this is your, we are between township and this slot is yours. Okay, these are, if you even go with the airplane over like Calgary in here, it was off. I didn't come with the airplane, I bet that happened. You once you flying from North Dakota to like Houston from here, you see these blocks. You don't see these blocks? You see them?
Yeah.
They were started.
I think there is one.
Those are township and range, okay? And those township and range, I think, additional, you know.
It does.
It does?
It's very well traveled.
Okay, you see those, lines, or that's how they define the well. How you know where's the location of the well? How you know?
You define it in terms of. Yeah, the X one. That's the coordinate. Yeah.
But the coordinate is what? Easting, northing is, international. But normally you work, in the field based on township range. Let's say the well is 1436 W
Yeah.
00 and that.
So the range are like that in the townships are like that.
Yeah, range are like this. So range are Y's, townships are X. And in every slot of the township, there are 36 blocks, smaller blocks. And every smaller blocks is A, B, C, D. Yeah, once you get to the work, you learn. That's how you find a well. Like, but this is the number. That's what I'm trying to say. That's 01 14.066324. That's how the wells numbers are in North America. And W4 is -0. Why -0? Because from one wellhead, you have 8 branches. So all of them have the same location. So they say -0, -1, -2. Okay. This well has a -1, but it was blanked, so we didn't model it. So you go -0, -2, -2. Okay. So you name it, rename it as to this, and now go on your trajectory. Do the same thing that we did before. Just copy paste your MD inclinations. But in this time, just don't copy paste. You have to put the right eastings now. So put the easting and northing right. You put the easting this. You put the northing this value. You have to put a wellhead. Like in dynamic design, you cannot just say 0, 0. It doesn't work. Like you have to, like in the one single well, trajectory is only important. So you can't. And then you put this, and then you put deviation survey and paste it, and then you put your MD. What is your MD? 932. And the Excel I say 932. So it's one well, you got it now. You can come over well here. Look at my screen, guys. Here, the field layout. And you see only have one well. So now what do we do? We go on the grid. On the grid of the well. And we assign the grid because we don't want to wait here for a long time. Just say instead of 20 meters, you just put 100. Okay? And the other thing I want you guys to do, you come on the pressure. There is a there's Excel file by name pressure, the BHP. the pressure is on kPa. So make sure your units are right. You get the pressure, come on the pressure profile, and I see here pressure kPa, and you paste it. Okay, that's the actual bottom of pressure measurements. Okay. So because we have 8 wells and all of them have the same bottom of pressure, because all of them connected to the same. Okay.
How is the completion in this kind of work?
These are open hole. We're gonna do it, but because we want to do it faster, let's do one well and copy paste it 8 times. Do it. You guys doing it? Just don't me doing it. You guys do it. If you do it once, then you learn. Like make a copy, make a copy, make a copy, make a copy.
Then to have the same pressure, that means they have the same configuration.
The same configuration? Yeah. No, the endpoint, the bottom hole pressure, all of them connected to one location.
Yes.
No, the configuration not the same. The endpoint, all of them have the same bottom hole pressure.
The same bottom.
Yeah. So change the names as you copy paste. So the first one is 02. Ran this one 3. You have to do it. Like I give you all the wells because I want you to do it. Like if you just want to make a shortcut, just do 3 of them. 6. How many wells we have? You have to do, I think 8. Yeah, do all of them. I just want to tell you how quick you can make your multilateral well. This is the actual well. It's not it's the actual well. We're gonna history match it also. But if you not do this well, like my history match is not follow your history match. So now you go on every of these, and easting, northing is the same. You just copy paste your trajectory and your MD. Okay, all of them. The only thing difference is the trajectory is different and the MD location, the starting of your horizontal. So I go on this one and say paste. What is 1136, and I close this one, go to 3, and I go to trajectory, and just copy paste, copy paste. $10.96. Come to trajectory. Oh man. What's that? $10.68. Do it, please do it. Please do it. You guys did it? You guys not doing it, just me doing it? $14.93. Okay. You're not doing it Friday? What's this guy name? I thought he's fine. Wednesday. 7.
Okay, I'm certainly fine. I look at me.
1117. Okay. 1055. I did the last one. No, 1055. Okay, now we have the wells. Okay, so you come over here and you got all the branches. Okay,
Okay.
so I have it, but I still have to put what? Permeability saturation for every well. Please do it. Rickson, you come and do it on my machine. Come and learn it. Come and do it on my machine. Good. Just stand there and manage it. We have a lot of managers. No chiefs. You heard that expression? Okay, come and. So we have these wells here. Okay. So now you have to go on reservoir and you come over here and just say, I want to read the file. And in this one, you have the current 0. So do it for all of them.
So
You do porosity, water saturation.
so I'll go here first.
Go on the what porosity. Click on porosity.
All right.
Click porosity.
Okay.
Just
Then-
read file.
Right. Go into the file. And we'll go to the 2, right? You just-
Porosity. Porosity 0. No, these are branches now.
So
And
this-
I put it like porosity 0.
Okay.
Porosity 0.
Okay. Copy.
No, just click
No,
on
okay. Open
Just
it.
click on it.
Okay.
And
All right.
go on water saturation. Like here.
Okay.
Water. And read file.
Wow.
Go on water. Like go down. SW.
0.
Yeah.
Okay.
Click on it. Click on it. Go on gas.
Oh. Then read file.
You just put 0 and apply.
Okay.
You get all of it.
Yeah, faster than Robson.
Apply. Okay. You just put constant number.
Okay.
So do it for all of it.
So
Just close this loop.
this one.
Yeah. No, this. Go and open the other one. Java manager.
Java come. Java. Come here you. So you finished what, man? Yeah, open the web. So we're finished. So
You
where's
just
where's the porosity? Where's the permeability?
is it per?
Yeah, perm.
No. You come on petrophysical
Okay,
and
properties.
go on reservoir. And come reservoir defined. And go on horizontal.
What about
The only thing you have to use gamma to see it on the top one. And click on permeability. And you want to read the form.
any option for, sorry, I think it's for good velocity or something like that. Is there any possibility of the good for
In this one,
Okay.
you
So-
want to add dual permeability, but not dual porosity at the moment.
Okay.
Yeah, you only have fracture
So
in Bellboard model. This
Okay.
is like, not many people use dual porosity, so that's why
Okay.
there are so many other priorities. Like we added like later on. Like Pro 2. This is a well 2.
we are dealing with the well too, right?
This is like airlines file, you have it, you want to load.
What was suggested?
Any software you have to load.
Read the file. Read the file.
Is that
Yeah.
done? Yes.
Read the file.
Really?
Go to SW. SW2.
oh yeah. So go in the lower composition.
Saturation.
Go in the lower composition.
So this one, we put 2.
So you don't have
The gas saturation,
lower composition.
the gas
Just go in
saturation,
your resume, delete and read it.
the gas saturation, should we put 2 or 0? So 0.
Zero.
Okay.
Gas, 0.
All right. And apply.
To all of them.
Now you.
That's why these guys, like, these guys have a solution.
That's all.
Yeah,
Then you go to the next one, right?
yeah, so you have a,
Actually,
okay,
you
Oh,
guys-
where do I go?
Yeah.
yes,
I thought-
yeah,
Plus.
no, close this one.
This one?
So.
Then we go
Now
to
go and.
Okay.
You guys on it, go on
Plus,
the-
let's go
you
plus.
guys have everything.
then you come
Go on
to
the-
petrophysics,
Yeah,
Here,
reservoir properties.
property.
go here, on here. So statistics.
Yeah, reservoir properties again, click
Where you
it.
going, man? Not loading.
And
No, that's it. Then go on the-
will
Yeah,
log,
go on the statistics, go on.
Petro-
will log.
Define. I think is it define?
G again.
No.
Just reservoir you define. Velocity, yeah.
Go see, change whatever you, change your,
No, we have to put this. We have to put it here.
right now.
Is it read and gamma or something?
Put something where range, yeah. You know what's not gonna take-
3, right?
You have it.
Put it like, yeah, you have to put it where you can.
You have gamma.
And then this
That is zero,
2. We have 2 of them.
zero,
Then read.
and put the range like
Then-
500, whatever. Put the nugget 0 and put the
Permit
range
3.
500.
Yeah, okay.
Put it for everything.
So the range is 4.
Then
Porosity.
porosity.
Range is like whatever you want. Range is
Five.
like a very maximum range that you see the very various variability.
This is good.
Okay. Something like this.
Oh man.
So we put,
I read. Yeah, so
Yeah.
that's all.
then go to the water stream.
So yeah, what is the facing?
Read file.
0,
SW3,
3.
SW3. Yeah, this one. Okay. Now,
Then go to gas.
Same
Yeah.
for permeability and for.
0. Apply.
Yeah, I do. Like for permeability, you want to do different.
Right.
Okay.
You go to close it.
directionals
4.
and do different
Will number four.
parameters and see how it works.
Petrophysics,
And reservoir.
reservoir.
Yeah.
Then define.
See
Well,
the numbers,
Yeah.
you have to change it and see.
then
You have
horizontal.
to see the chart now.
Then you click gamma use.
Yeah.
PEM.
That's what we put in.
Then read file. 4.
Yeah.
Oh, yeah.
PEM 4.
Yeah. Go back.
Yeah.
Porosity.
You sure you have a permeability inside the software? Go in your wells,
4.
Porous 4.
something not working.
Okay.
I don't have a permeability.
Then
You should see the variance.
go
If you don't
to
see the
what is
variance,
it?
then,
4. Read file. Select
no,
it.
no, you don't see the variance. That's
Good.
okay.
Oh, yeah, good.
then
4.
So I know what.
we are on what?
after
What
that,
water
so-
saturation?
SW4.
Yeah, go in your wells and
go back.
properties.
Gas.
You
Yes.
have everything.
There is porosity.
Because you can run it without even having your.
Then we go to
I think we have a.
we go to we close this 5, right?
Like whatever number you want. I don't know. You can run it. It's like- Yeah, check that, see your physical is already populated.
This is horizontal permeability.
Again, next.
We have it already.
None of you guys have a mouse.
No, you click this before read file and PEM.
Read.
Very
Oh,
good.
gas. Put the gas 0.
That's 5, right? PEM 5.
Put the gas 0. Do it for all of them. Do it for all of them.
You can select 5. Yeah, okay. Water stream. Read file. SW5. Yeah,
Make sure you hit the terms.
Then
go to the
gas.
gas.
Gas is 0.
0. Yeah, apply.
In every software, once you want to create a view model, you have to put your physical properties along with it.
Okay.
As a The only benefit here is we create the geomodel automatic.
Reservoir properties.
Define.
Present information. Read file.
So not read file. You go to use gamma and perm.
Okay.
Okay, we are on 5. We are on 6. We are on 5 or 6. Huh? We are on 5 or 6.
Yeah. 7.
6. 7.
I've given you that many wells.
Just see how you select.
The ones you have to get to know.
Then
Okay.
and then we go to property.
Practice it.
Porosity. Then read
Yeah. And 7.
7. We are entering the petrophysics.
Now run
properties.
your statistics simulation and it tells you what is wrong.
Sure.
Probably not having.
Okay.
Oh, yeah. Don't have those.
Okay.
Come down.
What is
Hit come down.
excuse me, these are the well names. When you open
These
it,
are the
there are
early
different
ones.
properties
Yeah,
as well.
fill all
So what is the situation? Everything we are entering in. Read file.
Hit the start geostatistics.
Establishing.
Not you guys. You guys, and it gives you a list of error you have. Those are the stuff you have to do.
Read file.
Yeah. So
What do you
we
click here? What is the situation? So yeah.
0. Was,
You have selected this. What?
yeah. Finish it.
Okay. So close it.
So
Minus. Yeah. Then well number. Oh.
you see, I told you that is 6, man.
We'll go back.
You guys work
Go back.
out.
Go back.
I told you that is 6.
Go back.
Could I please?
And the reservoir properties.
You don't need.
Yeah.
You just put the
Reservoir
actual.
property.
Yes.
Define.
So we come to define.
Yeah, define.
Then we go to our reservoir.
Yeah.
Normal.
Yeah. Define. Yeah. Click it.
Okay.
Click it.
So
Read file.
read file and then this thing. So
Read file.
yeah. Then 6.
Yeah. Good.
Permeability that we're dealing first. So we choose this one. It will read. Then we come back to yes, situation and gas. Yeah. Then we come and we read 5 and 6.
Pretty sure you don't have those.
Then we come to water situation. Read 5. Then we go to water situation 6. Then we come to our last gas. That one is always 0. I don't know. That's why it's
Okay.
yeah. Then apply. I don't know. I think it apply like that. Then we close that one and we go to well 7. Come and pick well 7. Then the same thing. We come to our petrophysics. And we come reservoir. Then we come to use. Then we take horizontal permeability. Then here, you click use gamma log calculation and perm. You click both and then you see. Then you come to 7, perm 7. Then
One of
go
these terms
to
are not complete.
this.
You have to go one by one.
Then porosity 7.
Very hard to get.
Then we go to our water situation.
Yeah, we
Read.
see. These are not complete.
Yeah.
You have to fill.
7.
You have to fill all those.
Then we come to our
You have
gas.
to have everything.
Then we put 0.
All the horizontal curves.
Then we apply. Then we close it. Our last one.
There is a lead file.
Then reservoir.
Which one you have? You have to go one.
We click this. And then this. And apply.
Which one?
Perm 8 last one.
Don't have a gap. The gap's zero.
Then close to 7.
Right? How many you
We
don't have?
go to
You click that one.
sorry.
You click
Yeah, I went and actually 7. Yeah, let me see that.
No.
That is for resistive.
Now go rate 5.
So 8. Thank you. If you are not there, so go to our as
Rate 5.
8 last one. Right. Then we go to our gas 0. Right.
Use gamma to see.
Right.
You want
So
to see the well. You have
on
the next one, do
yeah.
the process. Done?
Yeah.
Now go on the geostatistics. If you could, on the reservoir column geostatistics.
Geostatistics. Is the geometry down here?
No. In the reservoir. Reservoir here. Geostatistics. Bottom here. You come here, geostatistics. You have to put your paragraphs. Put whatever you want here. Just nugget effect normally is 0. And you put like whatever you want. I give you a play with this. And do it for all of them. And you can do it like if you want to see 400, and put this. Like Rickson, just see the variogram and everything. Like
So,
if you and you want to see it denser, you just put this 1000 and you see it more. This is the variogram.
So you play with these numbers with different.
Yeah, you play with these numbers to like normally in horizontal perms, the variograms is what like this normally. So normally for this case, I go with 1.
Okay.
And I don't trust this part, and I just go this one. And you go permeability. Normally nugget is 0. Sometimes people do it 0.2 or something, and you put the range of whatever you want, 500. But you have to follow this shape. This shape doesn't give you that, like you see. So this part is the geologist part. Do the saturation as well. You have to match it, you see?
Okay.
But this is
yeah, what's this? So
what is saturation? Right, Rickson sees all the right charts. Once you see it in variogram, that means everything works.
Let's put this 500 or
What is saturation? You have to put the number. So it sees this is gas on the bottom. Just say, you don't have to do anything. You just go 1. So you don't have a water saturation variability. And I think you have done, go and check all the water saturation and see if you put everything. Well, it looks like you did. Okay, now come down. Go on to computation. No, open it.
Okay, plus.
And just say start just statistics. The second one. So these are the parts that you don't have. Okay, so these are errors. Okay, so hit OK. Hit OK. Go on every well, because those guys already using the example they're already done. Go on the well. Go on the well.
Okay.
And come on the first one, for example. So you don't have an upper completion. It's right here. Okay, so you put a check mark or already does this. So come with the lower completion. Go on this one. Hit on and say add new here.
Add new. Where is it? Okay, yeah.
And concentric is okay. Go okay. Go okay. And come and change this to open hole. Right here, this one.
The doorbell.
No. This one. That's okay.
Look at all.
This one.
Okay.
Item.
Open hole. And I think put 6.25.
For the is it the ID?
That's the ID. Yeah. 6.25. And I think it's May 2021. Checking my PowerPoint to see what's the date is. Just in my PowerPoint. No, it's just let's use March 14, 21. So come in the software.
March 14th. You guys remember.
Come in the software. Just change 23 to 21.
The date.
No, just this one, the year.
Hmm.
21,
21.
no.
2021.
2023, 21.
Oh, okay.
2021. And hit this, is fine. And just go, April is just go one, March 14th. No, we pass it. Go, okay, go. Hit March 14th.
Okay.
14th. And yeah, that's it. You learn how to do it, and that's what do it for all the wells. You have to apply open hole completion. You have to add an open hole completion. Whenever you're done, just hit the start to statistics and it shows error.
Mhm.
That's the conclusion. If
Yeah.
it doesn't give any error, that's fine.
Add new. Okay. Then here was 6..
6.25, but you have to have open hole first. No. You have to do this first.
Okay.
I told 6.25. Go for all of it. You have to do for all.
And then the date.
Yeah. Just you go ahead and change the month. 2021. March 2023.
Oh, I have
Yes,
main tubing pressure.
Oh man.
Even
2021.
click
Main.
Just
Yeah,
click
main.
here.
So there is Excel. It has the
Okay,
PHP.
Not click that. What's it?
14. It was 14.
Yeah. That's it.
Excel has a PHP. There's Excel.
So
Example 10.
then we go to the well.
Copy, paste it.
The well 3, right?
Yeah. To fill the amount.
Copy, paste the. Yeah.
Okay.
Why you go to the.
Middle one. Right?
No,
Just over PHP.
You can click the PhD. 6.25.
Okay.
Right. Then the date.
Okay, this is the one. Copy, paste it.
Go to the middle.
Yeah, we need a time.
March 20.
Go in all of those wells.
Okay. Now go to the next one.
Go on the wells, open. Go on pressure for boil main tubing. And paste it. But you already have it. Go on the ones you don't have it. That error tells you like which wells you don't have. Hello. Yeah. What is the error? It's okay, like, you hit this one. So if you don't see this one, that doesn't give you. So that's a breakdown for every well. This is the average. You normally have to try to match it. So give some numbers on. Why you don't draw it? I don't know.
You can close the above the first option to make it easy.
To go from top, like, or get it, but because you don't have a very keyboard person.
Yeah, the first.
But normally you have to go from top to bottom. If you have an error in this one, give error on this one.
Second Friday is
But you see that your breakdown on it's number the number should be around 200. Have to,
No, I have the permeability diagram.
permeability version. Go on the geostatistics.
As well, that's the last one.
But it is,
Yeah.
holiday.
You don't have, you don't have, each of this one you have to fill it and then go.
Afterwards.
You know, put this as a number.
Yeah, because many people
You
will.
have to put this and then you can do this. There is a none show up, that means you can't have none. You can't have to have the directional first and then.
Done. Oh,
Right.
All
yeah,
of it?
yeah. Are we going to also do for the really frac? Because that one is also red.
So done?
Yeah.
Okay, let me see.
Are we doing for?
Horror fracture, we don't have it here.
Okay.
That's fine. And now you do this. So start your statistics. That's the first test we do. Okay.
Yeah.
And it takes long, so we don't want to go with this. Let it finish. How many reservoir breathing on reservoir breathing? And change that to 75 and calculate breathing again.
And then so click on
Apply breathing and come on the boundary.
so click on that contact. Okay.
Come on the boundary. This one is yours. Go on the no. No. Let's see how big. Okay, make it this big at 500. You just want to make the reservoir big. 500. Stop 500. 500. East and north something. Make it 200. And save as the model. Save as the model. Go on the project. On the project.
Okay.
Save as. Save as.
Okay. Save the project.
No, not that one.
No.
Save as. Like example 10-1, like the /1.
This
No,
one.
Like underline.
Example.
Example 10,
Okay.
underline one. No, we don't want to screw that up.
So I should just
You did?
like this.
Don't copy over. No. Hit on this
Yeah.
and change it to example -10, underline one. Underline. No, just after 10, underline.
Yeah.
No. Underline.
Like on the line with
Underline.
underscore or
Yeah.
Yeah, underscore.
oh okay.
It's on the A side.
Control plus.
You go to 8, you find it.
I have that.
This one.
Yeah.
Yeah.
No,
it takes
Okay,
one.
let's say 101. Let's say 101. And save.
101, yeah. 101.
And you delete the dot now.
I think underscore is in British English.
No, 101. 101.
No, we
One.
don't.
Okay.
You done?
Just copy.
You have a,
Yeah.
right? You have a.
Okay.
9 to-
Mhm. We call it on that because we are colonized by British now.
So go on this one. And. I think you have this one. There's nothing. You cannot put it. I don't know what you did. Oh, okay. Go in your open hole. I see. You're not producing anything, man. You did something. You're not producing anything. So you done?
Yeah.
Now you come over here and time a slot, and we put this as 500, and we just hit this.
Wait to run.
You save it?
Yeah.
You sure?
Yeah.
Okay.
101.
Just wait.
Mm.
If the first part of it is slow, and then go down. I just don't know how big you put the grids on the buffers. Just want to make sure. But everything is 100 because I don't want to.
What?
Yeah, you go to
What?
the-
That is say.
What is that?
I don't know. Low.
I didn't
System.
go to the-
No, that's
Is it not charging? Why is it charging?
no, it's not short.
What is the problem?
I don't know what's the grading you put because this machine is not fast. Yet. I just want to put it 1 meter on the well and put it over. You guys did it or not? Is that error? No. The start simulation? You did start simulation? But on reservoir grids. Go. Go on reservoir grid. 50 done. Come on the boundary.
Now you are reservoir engineer.
You become a reservoir engineer.
With the support of the senior reservoir engineers. I'm a junior. I'm the junior. I'm the junior. So you guys,
You guys didn't do those.
you guys
I
are.
think it's the same thing.
Go on the pay thickness. There is a thickness folder. There is Excel with a thickness folder. I give you page on
Yeah.
value.
Yeah.
But here,
Mm.
is that open?
Introduction to us, okay.
Yes.
The introduction to senior, what things are, what.
So we go to each
In
one
the
and
video, we can see
the
one step by step.
What's that?
Yeah.
Go pay thickness. Go on the thickness.
I have a different here.
Simulation
Yeah,
complete
Excel, copy
successful.
paste all of them. Let me. You guys didn't get the thickness. Also.
Yeah.
Let me go then the pay
Thickness.
on the reservoir.
Go to the reservoir.
Reservoir thickness.
Okay. What is the
Enable. Yes.
No, this is
So now you
reservoir
have the
thickness.
reservoir thickness. Now hit the reservoir simulation.
Reservoir thickness. Yeah.
Yeah, I give you reservoir thickness. You have to enable this one, enable variable thickness, and go on the Excel.
Excel.
Go on Excel. There is Excel name thickness, pay thickness, not the tab. Like there is a Excel name. Pay thickness.
Where can I locate it? Okay.
You got it?
Thickness, this one.
You got it there? Yeah. And run it. Start simulation. No,
Copy it.
Is it? Yeah, we copy over here.
Yeah.
Okay, when you go on the computation, go on the open the configuration, go on the simulation setting,
No, we have to copy
make
all.
that 2500. That's the number of final steps.
Copy all.
And run it. Start simulation.
Copy it.
Not the top part. But it doesn't matter. You do whatever it is. Yeah.
Thickness.
Paste.
Okay, now you got the thickness on your geo model.
Wow.
This is the contour. Now it starts simulation.
Start.
What
I
is
saw the
this?
simulation.
Yeah.
What is
Oh my
simulation?
God, what is that?
So normally, if you work with
Where's the
geologists, they give you that map, isopac map,
Start
and they give you points with the values and just copy paste.
So we go dynamic.
Concept.
Oh, you go
I wanted
dynamics.
to run this movie. Press yes.
You do very well, Kelly. Man, you something wrong.
It's like, it's like, petrol.
Yeah, the software is very good.
How do you say that? It's like petrol. Is that what?
Actually, it's yeah, and then at the same time, like prosper.
Oh, yeah, same time.
So,
Go to the.
What? Has it finished? It's running like that.
the bottom operation when you put the dates wrong or something.
It's this kind of this software. I need to extra machine now.
That's
So I need to buy it. My machine is not. I'm using MacBook. It's messing up.
So this is
That's right.
this is
Let me come and check you later. So now you guys run it again? Okay,
Yeah.
run it again, and then we want a history map. So you see how it works. You put the property for the wellbores and you put the variables. That's the same in a lot of software. But the thing is added on this, we create a geo model and we're gonna see the geo model, how the geo model looks like after simulation done.
Yeah, it's running fast.
And yeah, and one of the advantage and the main IP of this software is you can put the well grids small and reservoir grid big. You can put the reservoir. That's the only software in world that.
Oh.
That's the main idea of the software. And really, because there is a grading happens between the wellbore and reservoir, that makes it important for once you want to do well completion design. That's my tomorrow talk. I'm going to talk about it. Like that's becomes important. So then you go here and you have dynamic stuff. So you see something wrong with you, man. Like there's something I see. So by the static properties, this is your static.
Gradient.
Let me see. So this is your porosity, and this is your permeability. So you have, this is your permeability variation. You have more permeability variation, so you see more contours. Then go to the field results. Go on the field results, and maybe don't get there. You did something wrong. You see, you did something wrong. Like something wrong. So
I cannot rectify that.
yeah, I have to take a look and see what's going on. But this cannot be right.
Yeah, you learn this. Yeah.
Yeah, I think. I don't know what it is.
There is not.
I give you, it doesn't look right. You have to decline. The rates have to decline. This is a small box. You have to decline the rates. I'll send you the solution for all of you guys, and you guys go and check and see where you've done wrong. If you don't like the software treating or the geo model, you come here and you put your geo model yourself. And you have to hit this, and for every property, you have to put the table. Yeah, you put the table. And realization, forget about it now. Treating, oh, you guys did the treating?
No.
Treating?
No, we didn't do anything.
Go treating. Go on process permeability. Okay, that's right. That's right. You did everything. Go on the field layout and see the value study. Oh, rel current. So now go on the record. Go on the record. Put the NOW point two.
Point two.
No, there is a point two. 0.2. 0.2. What? Okay. Now start simulation. Yeah, I think you got so much rate.
Yes.
But it shouldn't be because of that. Like, you should get results faster. And the runtime is the best part. Like, has to be faster because we want to do on 15 and on. Okay, you guys can run it at least? No,
Hakim, are you getting the?
Let me see what's there.
Claudius?
Okay, you put this 100.
I want to go and take the pizza again. But now at the price I can't go and come and date it. Yeah, you say I like food. No, it's he told me to sit down. Yeah. Can do. From here. Then we will move to Harrington Hall.
And then go put everything zero.
Yeah. Ghana University.
One of those gang members.
Yeah, I stopped you when you were calling dollars with one guy.
Romanian process looks okay, but let me see if these guys, if that's the only thing they've done wrong, or the other parts. Come on the field results, come on the results.
The bottom.
And go on the field.
Fourth one.
No, I can't do it. This is wrong. Okay, I'll send you the solution,
Okay,
and then you guys can go and check where you've done wrong.
correct.
Because I want to teach you how to use the decline rates and other aspects of this. I don't know where I put my example. Go on my solution. I think I put a solution somewhere here. Just let me. And I put a solution. Oh no, not here. On this one, simulation course. Oh, I have a 14. Open 14. Let's see, like that. You can't. You have to load it. No, you can't hit it like this. You can't
Okay.
hit it like this. No,
Oh.
you have to go on top and load.
All right. Where do you load it? Where do you load this?
No project, the fourth one.
Okay, so
It's send deployed. It's send deployed. Because your unit
I think,
was.
is it this example?
Solution.
This is wrong.
What is this solution?
Oh, you are the only one I think you're close. In all these softwares, because these are not well connected, you have to put these.
It is in the digital.
What?
Larger numbers.
What is the
because they get the rate and then go reservoir. Get the rate, go reservoir. You have to put the small times.
What is the folder name, please?
Digital.
That was the desktop.
Yeah, desktop.
Put desktop, take desktop.
I see a simulation. Simulation. No. Simulation course. Solution 214 solution.
Good. It's ready now. So
Which one is that one? It's a gas one. Oh.
so
On the break, I'll find you that answer. I didn't bring it on me, I think. I'll send you guys after the solution and then you guys do.
This.
You got the rates? No, that's not right. You have to decline. Rates have to decline. Like, yeah. In the PowerPoint, you see it, like, the answer. You're close to it. You did
oh
something wrong.
man, I want to publish, man. Let's publish,
Okay.
man. I'm working on. Oh, man. Damn.
What's the bottom of pressure you guys put in? Like, go on the bottom of pressure, like, see if the units are right. Because the Excel is what? Go bottom of pressure. Go your bottom of pressure and see what's the bottom of pressure.
Congratulations, man. How many people publish? How many publications? Yeah, what the publish, man? Get out to like to that. I told him and he's
I don't know, like one of these units is listed wrong. Like,
this
also one
it's a very good system, yeah. I
No.
the last time. Very good.
Oh, that error you get? Oh, no, minor, like, you can't really put the, you just want to tell you, you don't have a lot of saturation. Very low.
So
These ones are additional use.
okay.
So now go on the gas, you go on the example, like, can I control it here and see what you guys want to do?
Yeah, I think you can.
Yeah, the controls.
Let me just go and then you guys sit here and do
Yeah,
the
please.
example.
Yeah.
Yeah, you guys do it here. So the answer should still look something like this. You see your well pressure looks like. You have to see your pressure inside the reservoir. Then we want to do the history match. Like we couldn't do it because we couldn't get the rates. So then we want to do the Monte Carlo simulation. Let's forget about Excel and then let's go on the gas well. We don't do the Monte Carlo. In the meantime, I see if I can't find the file, which I can give you guys and run it and get the Monte Carlo. Because that's the continuation of this. So we go on example 14 as a gas well. We want to calculate erosion in the annulus. You know what's the annulus? You have a screen and annulus, there's a gap. That's a big issue in Charlotte. That's a big issue in North Sea erosion once you got the higher rates of gas. So everyone follow the PowerPoints, and Rickson, you come and follow this. Example 14, you go and get the solution. Come get the solution. For that one, I bring the solution, but for this one, you just go based on what it said. So you go based on the PowerPoints here. Everyone's follow the PowerPoints. The only thing you have to put here, you have to put the upper completion, and you have to put your erosion property. Go ahead. So open the PowerPoint and see what you have to do. And you gotta do the same thing.
Call that guy to come.
You can go with them.
You come. Senior reservoir engineers.
This one I give you most of the. The problem is I didn't bring my solutions. I have to find for the solution.
So you become a selector tubing.
Open example for. Save this. Save it, and then
Where is it?
I send you guys.
Tubing configuration. We only did this one, you know. Click on this. Completion.
Add new completion.
You go to new completion. New completion.
Completion. Where's completion?
So this is a gas reservoir. Most of these erosions have been the gas. Okay, go on the lower completion. You guys did it.
Lower.
You guys did the lower completion.
Completion, yeah.
Go on the lower completion.
Open
No, run on the producer. Under the producer.
it.
Producer.
Open it.
Go on red ones, open it, and go on the lower completion. And you've done that exactly the same thing. But now you have to do the open hole and also the screen.
Seems like this
Why we take it?
No, okay, the screen is different. Case hole is case. The screen is like something they have hole and they have a wrapper on it. And because there is a communication between that and
This one, isn't it? We should change it. So we change it to 16.
Somewhere goes here, somewhere goes here, and that's called the road.
2022.
Only this software and not software model. Again, the specific.
What is it that is in there, the number?
Okay, see in the, okay, you concentrate, put the date right.
2022.
And
Is it
then
December?
go,
Yeah, 16.
you have to put.
December?
December 16.
Oh, 29, 22, no.
Yeah, this
Oh,
will be not here in this date here now.
so what? 16.
December 16.
What's the ID? We should put.
And then hit next.
Should I leave the ID the same 7 or I should change it?
I don't know what's in the PowerPoint.
Okay.
8.5.
No, I don't think.
The bigger the analyst.
Yeah,
the more
8.5.
erosion.
It's 8.5.
Yeah,
8.5.
yeah, and then 5. Yeah, 8.5.
8.5.
So we add a new project or we just
Open example 14.
The next.
load it?
Just
Yeah.
load it. Yeah.
Mhm.
It's a gas reservoir. It's,
Next, yeah.
in the
Go down,
meantime,
go down.
let me find the example,
No.
the solution for you guys. Once these guys done,
8.5.
find the example on the break and I give you, because we want to do.
So next, and then we enter add the W.
Yeah.
Go on the, just hit next.
Okay.
And then see the liner screen. So now you can have all the screens. You have to add perforated screen.
Yeah.
It's the wire.
Remember these numbers.
Okay.
500, 10, 100.
And you have to put all the dimensions right. Like that.
So I have this one.
Okay, go on the producer.
Pardon me.
Follow the PowerPoint.
Yes,
But,
there's
go on
one.
the
Click.
producer, go on the word completion.
Open.
Add,
No. Supposed to be screen.
add, and see what I said. concentric tubing, and then
100,
it's open hole with the screen inside.
100.
And you have to hit properties. This cannot be right.
Yeah.
Okay.
Or you put those right.
No, no, we're going to change it.
Then,
Change this then. Change it.
now
So
this
the
is
completion
this
part
is
of the software is
1000.
like
It's 1000 rather. 100.
100.
you give the joint length, you give the numbers.
Remove 1 0. 100.
And then comma. Once you finish, you have to change ID. You have to first change ID and then OC.
The same thing.
7.
The same things.
Yeah, 7.
Same thing.
Yeah. You go to next one.
And once you finish, what is the ID? You have to be smaller.
Yeah, that's what is in the presentation. It's like,
What's the number? 7 and 7.3?
yeah.
Yeah.
Okay, just put the, no, go on the next one. Okay, go on the properties then. Click here,
The first property.
Okay, properties.
Yeah.
and then fill it based on what's the examples.
20, 0.9. That's 20, right?
Additional thinking.
0.9.
And this one is what?
Yeah.
So you know this part,
9.
this part is important for the gas.
I don't know.
This is a lot of erosion by analysts. So you have to model the flow comes in the analyst.
It's 400 roughness.
No, it's IE6.
IDs of the lead, some of it
My
the flow.
6.
So there's only two software models, like this one and there's a net
1.
that's model the erosion inside.
So for the line stream. Okay,
Is it open home?
What?
Okay.
IE what?
Okay, so
600.
600.
and then
No, I don't think. 606. Oh my goodness. Jawa, what are you thinking, man? I have to check. I won't believe you, man. Then where do you apply? And we select
So you have to hit these solve
in the
and
settings, select solve annular.
solve and in the setting. Make sure you guys do it.
Where is the settings?
And then
Go to the slide.
in the once you guys firstly run it, then you go in the erosion
Go to the
section and you choose your material
Go to slides.
and those.
So we are going to select settings.
Yeah.
Settings.
Okay.
Select.
The summary
Go
is
to
all
In settings.
Primary local.
In settings. Go to settings.
also
Yeah,
model.
that's where the settings are.
Actually.
Okay.
Some people call it PULSA, it's also, but it's actually OCOM. The person who developed this OCOM.
Where can we get the
Yeah.
settings?
Excuse me.
You did everything, you did properties.
Yeah.
Okay. You put dates right?
Yeah.
We are going to look for the settings.
Setting is on the top.
Okay.
Settings.
Yeah, I've seen it.
Yeah, now you can get.
Go on simulation.
Yes, yeah.
You have to put a check mark. Already did it for you.
Why are you doing this for last way?
We do this calculation for oil well, but we don't calculate erosion because
Yes.
no one's,
Why are you using, why are you?
because erosion for the gas, because the clients only wanted to do it for gas, never asked us to add it on the oil. If it's someone out there, yeah, but
I think,
your salt can go into that.
Run simulation.
That's why they don't do it. That's it, yeah. So,
Simulation is ready.
because that's, that part is very iterative, concern, because we have to, we do the grading at the end of the well more, because the flow comes and at the
Gas
end
well.
has to go.
Open the
We make
simulation.
the grading at the end way smaller,
Let's see.
and that part takes a lot of
We
time.
can
to
find
do
out
it.
the
What is the well? You say that well, right?
For oil, they don't, you don't calculate oil because no one really has the erosion, but always want to compare it to
evaluate
IC.
the
You want to have a
Yeah, so
screen
this
to
example
see how it's
I think there should be at the results.
They don't use it for anything. It's just, I don't know.
It should be
that's
at result,
typical
right?
vendors.
We,
They do
okay,
it,
yeah,
but
go
they're
to
not
results.
using it. Like, they don't get any benefit of it, but
Um,
okay,
this
run
will
it.
be lower completion.
we have finished
Go
one.
on the lower completion,
Lower
Yeah.
completion. The
lower
first one.
completion,
First one.
and then come and instantaneous,
Yeah, the second one.
and then go in a screen origin,
Screen rose.
Yeah, this one.
and these are screen velocity. Go on the reservoir analyst.
The second one.
So this is reservoir analyst. So this is what you get in the reservoir, and this is what the analyst comes.
Mhm.
Because some of it comes and go in.
Mhm.
And now we want to make this more in the analyst. Go in the SC completion and come next. And go here properties. And then change this 5 to 2. We want to make the holes smaller than the analyst. And
Okay.
forcing everything go in the analyst.
Preferring ID. Okay.
Apply.
Then
It's
apply.
fine. And then come and sand, like come up on the producer, or on the not sand production model in the producer here.
Yes.
Say yes.
Yes.
Then you have a stainless steel, okay?
Mhm.
So you can choose the different stain. You can use a tungsten carbon. No one's had a tungsten carbide that line. So everyone have a stainless steel. But you can do whatever. But you can make the particles bigger. The particles are function of your sand, what's it called? Sand control system.
Mhm.
So if you make this bigger, the sand particles become big. So make it 900.
It's like a thin screen.
Huh?
It's like a
Sunscreen.
thin screen or.
Yeah, that's a sine screen.
Sand control.
Oh,
It's there's like a slotted line.
oh,
You can put a sand screen, like come and change it sand. Say wire wrap screen or premium screen, whatever you want.
gravel painting.
No.
Do the gravel. Whatever you want, there is a equation based on the size. If you put a gravel pack, go for gravel pack.
I think that's a common one.
It's asked for the gravel pack D50. You see? And calculate the D of the particle based on that.
Mhm.
So I can't give you the formulas. And the picture on the right, look at some DTC. You were the geomechanics guy? Yeah. So DTC and DTS, you were the one. Like, just show me that geomechanics.
Oh,
We got
No, the compressional and the shear, wait.
oh yeah. So you know the one? Show me the static. Show someone. Here. So here is the parts. And normally companies provide the physicals.
Mhm.
So increase your DTC and increase your DTC, but not more than DTS. Like make it to 10 and see how the red line changes.
No, DTC.
No,
the first
DTC,
one,
the comparison.
210.
So is it changing the horizontal?
No, change it red line. Then hit on it and change on the D. You see it goes like, go on the D.
on the what?
Lee model, like, put it back at 150.
Okay.
Then you put it like, it wasn't, put it 150. And go Lee model, change the Lee by its function. Like, to change it something, I just wanted, you change it and see how the red line changes.
So let me use a
Yeah, one.
Change the, what do you do? Don't change the byte, just change the model used for byte.
Yeah, you pick the second one. Second.
go to this one.
You see,
Yeah.
this one is changed. So this is the bracket you got for the sand production, okay? So if you go here, you start sand production. This is just representing what's the sand production happening or not happening. The software assumes always sand production happening once you do the sand erosion. Because the erosion rate it provides erosion rate as a function of sand you produce.
Mhm.
So now I'm going to start simulation. And go on the lower competition, then once we finish. These are additional, these are not mine. Go on lower competition, go on the stand biggest, go on erosion, go on erosion. So now we see we make the, no, go on stand. You see we make the hole smaller.
Yeah.
It was 5, it was big, like everything goes inside the pipe. Now we make it smaller, more goes in the annulus. We got more velocity, and we have more erosion. This is erosion. And the unit is what? Millimeter cube per kilogram of sand. So the software assumes erosion always is, but you have to give the function of how much sand you think you produce. Okay. So it doesn't have a geomechanic model to produce the sand. That's a future thing. But now it just gives you amount of erosion based on the sand. You see it, how it works? Now go copy this example.
Which one?
Copy, okay, go on the top. Everyone, go on the top.
Just click on it.
No, here, like this one, click this and take it up. Click right on limited entry. Click right on this.
Yeah.
And make a copy. Click right. Click right. No, click right on this.
Yeah.
Okay.
Make a copy. Change it to condensate. Click right on it. Say condensate.
Rename it.
Okay.
Rename it. Condensate. The other one.
This one?
Yeah, rename it.
Okay.
Condensate. No, not the first one.
Yes, I know. Condensate.
Condensate. Whatever name you want. CONDEN.
Yes, you are indeed.
Now go
Where
on
do
fluid.
Condensate is indeed.
Now go on.
Go on fluid. You guys follow the PowerPoint. Follow the
Fluid.
PowerPoint. And put the composition the way I put it in the. Go to fluid, change fluid, go gas. Fluid.
On the
Inputs.
Okay, yeah.
Go on fluid, open the input.
Okay.
And go on gas. And change that dry gas to condensate.
Condensate.
And now go on my PowerPoint and put the composition. There's a composition tab. You have to. No, you didn't have a gas. Go. Okay, gas composition. Hit it.
Yeah.
Hit it. Hit on gas composition. And now fill it with the. See what I said in the PowerPoint. I think I said the change C7 or something. And increase something. This is Monte Carlo simulation. You have to come way up, down.
Have you seen the condensate?
No, go after.
This is one.
So, find the example for T.
This is gas condensate. Should be here.
I'm plugging in this one.
You put the gas composition. Then you put the gas composition. You put what I said. Then go on reservoir temperature. You look at the reservoir temperature. See with the PowerPoint what I said is the reservoir temperatures.
I follow this. And then just something.
Oh, you see the second, the previous example?
Yeah.
This is the previous example. Okay, just start simulation. Done. You go on the top. Go top. No. You get settings. Go on the simulation. You already have it. I already put it here. Just start simulation. Did it?
We can find those the condensate air composition.
Oh, when you start to come down, that's great.
Let me find.
No, it's here, man. This is a fracture one. For
Yeah, here check. Okay. Okay. Yeah, it's
and I said C1 to 45. Just wanted to reduce the C1 because if you put C1 less and you normalize it, the things provide more condensate for it.
so C145.
And just say, okay, we normalize it itself. Yeah, is it okay? And go into reservoir temperature. I think your reservoir temperature is not there. See what's the reservoir temperature. I said you should go on the reservoir.
Here or coming here.
In the reservoir.
Oh, okay.
Go on
Temperature.
reservoir model. The temperature of 1 Celsius. So see what I said has to be. It's 80 or 100. No, come down.
Down.
No. Come here.
Okay.
Come after like 2:30. Come. What I said is temperature. I'm pretty sure what I said. Okay, come here. It has to be 150. Put it 150.
150?
Yeah, put it. The previous one is 80. Go the top one. Come up a bit. No, not up. Okay, maybe it's here. Like this. After, can you explain?
Yeah, 239.
239.
So one more. It has to be temperature problem. Okay, let's put 80. Let's put 80.
80.
Let's put 80. And go and look at the fluid gas condensate shape. Go in the gas again. You see it's on the gas zone, okay? So go on liquid droplet. You see how it works. It comes and go down and go on to the properties. So this is what. Okay, save this and run it.
So save it first.
Save it first and run it. What number you put up pointing at the
So what? Yeah, 80.
80. Okay.
Yeah.
Run it. Now save it with one some name.
And
Not
then
in my folder, like somewhere else.
okay.
These are the dots. In the test.
Okay.
Just say your name or whatever.
Correct.
Yeah, 102.
And run it, and then change the temperature to the lower temperatures.
102.
Then you have all you running. No, what do you can? Which one is this?
The first one.
Where's run simulation?
Is it San Erosion one?
Go down.
Boy, it's not going down, man.
Where is this? Where are you?
You can go out. That's all.
Yeah, if you can hear me. Can you put it inside?
Don't go and press anything and then this thing. You just
And now you have to explain it, guys. Like, don't just go.
Wait.
Come over line.
Say which word.
We don't have open book, okay? We have to put something.
Because it can be
And then
No.
here.
You have to do simulation and get your results. No, you
Oh, so this is the simulation that's on.
Then you see. These are okay? Yes. And then you see that this is right. Okay. Simulation setting is good. Yeah. Okay. You guys did it?
we can see the simulation.
Run simulation.
Yeah, It's not showing. Run
It's not
simulation.
Showing up in options.
Now calm down. You the laugh. Why you laughing?
I think option deleted.
Brother, stop saying that me. You, huh? Oh, okay.
Yeah.
All right.
Oh, okay.
Ah, yeah, I've
So
seen
that's why
it.
it's over here.
This guy is not helping us. You see that you're accusing me.
Come over here.
Yeah, you're accusing me.
Over. That block. And then run it.
I'll go to the results. I'll go and check the results. This now. This now.
Okay, that one we do like
Just oil and gas and improve
Okay.
products.
So now, yeah, I can help you.
The vertical.
So you see, like now, it's erosion is bigger. See, because you make the hole smaller, the flow goes in that one. The ID of the holes inside the okay. So that's
I'll work with this guy.
and then I said copy
I have to work with them and produce. But you are not. I say we should write the paper and start with him.
and then
He's
this
a
one
very
will
good guy.
go
So get here.
and they come over
get
here and
alpha.
say
Then work with him.
and say like and now instead of 64 drop it to some 40 and normalize it and say okay. And reservoir temperature is 1. So you come and say, okay, my reservoir temperature is wrong. I'm going to put it as 80. And then I go back to my fluid. So now I have this. And then I come over here and see how things are. Liquid drop up. Those things are changing. And now, what is the PVD cap? Yeah. And then, so, and I said, so now to put it, let's put more C7. Like a condensate, like more these shale oil stuff, yeah, everyone look for more C7. So now you're in here instead of here. And you take a look at here and see what's this. So you have to explain. You take the PVD first? No. So this is the bubble point. So you have to come from what? 100% liquid dropout. That's what you 100. You take that one? Okay, for example. PVD thermodynamic. So, but if you put like 150, and then come over here, the upper is here, and this is what's happening. It comes short and then goes down. It doesn't, it's because the number of temperature is, if you drop it like you see, that it's a sharp change here. So it's gone from 0 and then goes up and comes down, okay? And, but the other one was 100% because this line is 2 points, so you increase. So then say, okay, now you do everything, just go here and save it. So example,
The software needs a strong machine. By the way,
so just condensate. Okay, condensate, and this is safe. And then say, okay, how many simulations in and say run? Zero. And then once you run it, I just want you to see the flux. You see the flux. You come over here and see the flux. For this one, you go and get a condensate, you're not solving that. I don't know why it was the what's the term of this? Flux is very tiny.
This is seven. Okay, this is 7 validation. This
Mm.
one, my one is 10 generation. 10 generation. 10 generation as well.
Because randomly I put it, let's just say 80.
Long term release.
80 here.
Tomorrow, I'm taking the same time.
Like tomorrow morning, I can make it.
You guys get it? Oh, you're still running it?
Yes,
Yeah.
That's not.
Maybe we can check right, but I think it's taking time now.
Oh, yeah, like, once you do compositional, because it was a dry gas versus this, but it's done.
Oh, okay.
Now go and see your load completion results. You do the same. On the load completion. Don't eat that too much, like it's loading.
Okay.
But later. That's fine. That's fine. Okay. Go on the instantaneous.
Yeah.
And no, go on the pressure flux. So you see the flux, you have the condensate plus the gas. You see this orange one?
Mhm.
Click right on it. Click right here. Go chart setting. And cancel the red. Apply. So you're producing condensate.
It's not
Close.
okay.
So now you see the condensate, okay? You see some condensate. And this is the case, it was 100 feet there, at all, huh? So now go change it to 80. The temperature, that's our model. Go in input here, not that one, we're going to this case.
Input.
Go on input, go on reservoir, open the tree. Go on reservoir model, the top. And your temperature is 80, change it to 100 feet. I'm going to look and see where that looks like.
Go to
fluid.
fluid. Where?
Fluid.
Okay. The gas.
No, yes, yeah.
Yeah.
So you are here. So what is this? You're above the supercritical time. So the software cannot use this for gas composition calculation. It just goes automatically to dynamic mode. So go in your composition. Go into gas composition. Come and change C7 to 25. 25. Apply.
Okay.
Okay, now we make it more fluid, like we make it more composition. Come in the liquid dropout hierarchy. So you see what happens. It comes from the zero, create condensate, goes here. Okay? So now if you go back to phase envelope, it goes from the zero. So if I change it to 80, change it to 80, you see what it is.
The temperature.
Reservoir model, change it to 80.
Yeah, reservoir model. Go to the gas.
80, and go back to the fluid. Everyone look at this.
Go to the gas.
And you see right here, go on the liquid drop. Just kind of, this is the error.
But here temperature is revolution 81. Change it 150.
Change it to 90. Change it to 90.
Yeah, temperature is 80 then.
Change the temperature to back to.
No. What is your temperature?
I think we change it
Here
to.
is showing up 80 and over here we need to change it to 150.
Yeah.
Okay, do 150. Do 150.
Make it 150.
We changing it here from here.
No, reservoir model. Go to the reservoir. No, you can't change it. Go to the reservoir model.
All right.
Change it 150.
Yeah.
And now go and run the simulation.
150. Yeah. Integrate. Yeah. 150.
Now go and run the simulation.
150.
Yeah. 150.
Yeah.
Run the simulation. And you should see condensate plus the gas.
Go to computation.
But if you go below the
Computation.
bubble point, now you go. Yeah, you see condensate. And now go and do it in the lower temperatures or the high temperatures. You should see different. This is, you don't see gas, huh? This is lower temperature. Yeah, it is 80 K. The temperature is 80 K. 80 K. Yeah. So increase it to 150. You should see gas and condensate coming. Because you go below the temperature, everything comes as condensate. Okay. Most condensate reservoirs, you are passing the dew point line. Yeah. But the software doesn't understand it, but you have to have the right temperature and right composition. Do 150 and check the gas because every of you have a different composition. You guys changing the composition. Go in their gas and see the composition if you pass in the dew point line.
Have you changed the composition?
No, you can't change it here. You have to go on reservoir mode. That's for information. Reservoir. You're lost. You're lost?
Yeah.
Where?
You guys are lost. Friday?
You did the erosion part. You did the erosion part?
Yeah. See, this is your stomach. You want to make calls.
Go in the gas.
See your stomach. We feed you very well.
So that's what.
We feed you well. How? It's not true. It's true.
I'm just teaching you some sort of what you do. So you come from the default, you come from this point, and then you start building the dropout. So they're running. They're running. Oh, these are
Why you say that? You are my friend, man. You shouldn't be supporting him. Man. No, everybody eats. Don't be.
Cancel those annular close below support once you're doing the composition of. You guys did it? I think.
Yes, yeah, it's running now.
Yeah. So if you don't do it, it doesn't run because we didn't code the software for condensate. We only code it for the gas.
Okay.
So now we do fracture, and hopefully I find the file I can share with you guys, and you guys do the month.
Okay.
In high temperature, I have no problem.
What's that? What's that? Iran? There's no condensate and it's a gas, huh?
There is a gas.
Yeah. Depends on it. Probably you have some condensate. Probably it's very end. Oh, you got nothing, man. It's something wrong. It's something wrong. Oh, because you see the condensate here. Send me your file. Save as it and send me your file. You show you produce condensate, but it doesn't show in the files. Maybe it's a bug itself. Just save as it and send it to me. Or email it to me the file. Save as it and
So it doesn't show it?
It probably has it, but in the plot doesn't show. Because in the other plots, you see the condensation producing. In the cumulative chart, going instantaneous. You want me results? From the result. One instantaneous. You don't see anything here, but go on the reservoir.
This time.
It's showing and producing.
So it should be.
Yeah, it shows everything. But there is a if, it's something that flux. Doesn't let it show. Send me that one. That's a bug.
Oh, your laptop is still in Canada time. So it was confusing us.
yeah.
Yeah. You know, when this guy came in and said it's 4 o'clock, we checked here was 3:60.
When you guys work
Yeah.
around. Okay, so that's why a lot of things we do is not compositional modeling. Like you do, if you model the eclipse, how many of who run the eclipse here? None of you? You do? 100 or 300?
300.
You really did it 300. Wait, what was it?
For your thermal purpose, I use 300.
For geothermal purpose.
Or for SGD or for SAPD drawing 300 or CMG stuff.
Okay, using E300 thermal.
Yeah.
Okay, that's different. Yeah. So there is a E300 thermal, but no, there is a compositional E300 and there is a
The
E100.
composition is that.
Yeah.
But we can use the 100.
But no one does. No one does E300. Why? Because it takes forever to run. Like that's what I'm saying. Like this is an example. Like how fast was the gas? You guys run it, you get the result.
Yeah.
Once you go to composition modeling, especially with our software, because we do the composition in the pipe, we do the composition analysis, it's always flashing everywhere. Like inside the reservoir, it takes forever. So that's what I'm saying. Like no one's really used E100, E300. Everyone was 200 because it takes forever. So that's what I'm saying. Like, but don't use Eclipse thermal for SAGD, man. You're from Venezuela? Where are you from?
I'm from Peru, but we use from Venezuela and Ecuador, all the horizontal wells, we use ACD or model.
Yeah, thermal Eclipse is awful. Like it doesn't give you that
Oh,
answer.
no, we use another software. But.
Yeah. Even T-Navigator, which I like, the thermal part of it is awful. They don't really, you can't trust them. Okay, that chart is, Rickson is showing is a Bexville, so in the horizontal. We try to be sometimes academic, and sometimes you use the flow resilience. This is in the horizontal section. Well, it's funny, it doesn't show any points. It has to show the points. Maybe that's another box in the gas. Okay, now we want to do hydrofracturing. Go open example 15.
Below.
This one is so easy. Example 15. You have to go in my Mazda simulation code. Go in the simulation code. For example, we have example. Okay, that one no. But don't save over because these are files I create for you guys. You're saving on it. What are you doing, man? Cancel. Why are you open? You have to load. Load the file.
Yeah.
Load. You want to save it?
Okay.
Don't save it. Just open. Open example here. Go example 15. Go on the well. Go on the well. This is the shale oil portion. Hopefully, once I come and teach this stuff, but I think I have to change my style. I have to give you a solution. I have to be prepared for the solution always. Half of us didn't get to that. So go open the test. So before you go to the test, so the shale oil is, I just want to go through it, like not teaching it, but go on you have 3 elements in the fracking model. You have a perforations, you have a frac fluid, and you have a prop. So open the perforation. No, on the top.
This one?
No, here. Like yeah, open it.
Okay.
The bottom. This is
No, go
open it.
and open the second one.
Open the second one.
This one?
No, open the first
here,
one.
there's the plus.
Yeah,
Oh, okay, I'm seeing it.
And go in the perforation model.
Okay.
So this software is like objects. You can create as many perforations as you want. You can have as many fluids you want, you can have as many problems you want, okay? So if you want to do fluids, you ask us and give you a library and you do it, but here assume you don't have a library and you just want to create your own fluids. So in perforations, you have different, show the phasing and those stuff, like number of shots, so you can play with those.
Yeah.
Up and down. So you fix your perforation, you go in your black fluid. You have to have it going on the model. So you say Newtonian or non-Newtonian. If you do non-Newtonian, go non-Newtonian. And go in rheology. Then if you come non-Newtonian, you have to provide time versus N index and K index for the temperature. So back to the model,
It's N and K.
N and K versus the time.
Harshal Berkeley.
What's that?
Harshal Berkeley or what kind of rheology model?
This is a power law. Everyone's using power law. Yeah.
You have any data for that? We have data for it. Like,
No, in this case, we just want to do water. Yeah. In this example. Yeah, you have to ask me and I give you the library you want. But go back to change it to Newtonian. And go back to rheology. And then in the Newtonian, you only have viscosity as a function of temperature. Okay. Yeah, that's all. All the software, the maximum they go into. And then go on the properties. You have to define your properties.
Yeah.
And also that's comes with the library. You can have a sand sieve of this and this, but really this is for more student like version. Go on the model. The things you needed is the mean diameter, specific gravity, magnetic constraint, which is the maximum. This is for every property. This is not something software to provide you, but they have a hidden number inside the library. So that's a maximum concentration that you can porosity you can put. And you provide what? The permeability. This is for after the fact. Once you want to model the reservoir simulation, you have to have a permeability as a function of crop width and the closure stress. So the software calculates the closure stress, and based on that stress and the width of the fracture, they calculate the permeability based on this table, and they put in a solution. And go on the type curve. This is the curve like some people in competition, a lot of people who use this, who run the fracture. A lot of you. This is very common fracture chart. Software doesn't provide it, but people using it. This is like for every problem with and like you have and you can call it universal chart. Universal.
There is fracture conductivity chart?
Yeah. They're using it, but they're not in software. But you have it here. You can change it here, and you say give you the optimum half length and optimum width. These are the actual values come out of this curve. A lot of competition engineers not running simulation, just using it. But okay, that's a part one of it, design of the process. Go now in the test, go in the well, like input, open the well. The other parts is similar to what you did on water flood, but this version I give you don't run it because this is under development. I just open the fracture for you guys to run. Go on the well and open the well one production.
But it calculate
Go on
The-
water fracture.
but it calculate the fracture propagation, or you have to
Yeah, you run it. Fracture propagation. Yeah. Okay. Go on the fracture propagation. Go on the fracture models.
first one.
So these are models that it has. You can go and drop bars and play with those. Go in my PowerPoint and explain ELSA. Go. Come on, this. So there is a model called ELSA. And that's very academic. And the problem is it's very hard to put it, and it's very slow, but we resolve the issue with it, and we had it. None of the commercial software have the ELSA. None of it. It's only University in France. I don't know. They code it in Python, and they have a Python code. But we are the only one. What's the benefit of ELSA? All these software that we're using, like Gopher, Crack, I don't know, whatever software you use, like even the Schlumberger, Visage ones, they don't care about the toughness. What they care about is how much fluid you put in the fracture and how much leakage you got to the boundaries. And this is a material balancing. I say how much is this thing's open up based on this. And that's all they do. They don't calculate the toughness because the model they're using are kind of old.
The toughness of what?
Who doesn't know toughness?
I know
You are
toughness.
the only one?
I know toughness, but I don't know. You are looking at it. Is it the toughness of this?
Yeah, next one. Oh, next one. Let me explain the topics. Okay. So we have opening and closing of the fracture, and that's a function of elastic modulus of the surrounding versus the location of that grid inside a fracture. If you are closer to the point of perforation, we are stiffer. We are stiffer than the parts are far. Like that's because of the shape of the fracture. Okay, that's because of the shape of the fracture. If you're further down, your effect on the stiffness is less than these ones. There is another component is toughness. And by say it's a fracture toughness. We have 3 fracture toughness. K1, K2, K3. And no one in the world cares about K2 and K3. K1 is, we call it a stress intensity factor. So it really tells us if you open this fracture by this much, if this is opening or not opening, really, in the tensile. And they have a shear and they have a tearing, which is K2 and K3. No one cares about those two because those are, they say, secondary. Some people care, but we don't care, and none of these software does. So the thing is about the toughness is the propagation of this fracture of fast. You don't have much time in creating hydrofracture. You pump this stuff, there's a competition between the loss and competition between open up. But the faster you grow, you have more volume available for this fracture fluid comes, okay? That's you get bigger fracture. So ELSA, really, the model has the formulation for how fast the front of the fracture is growing. So in the other softwares, in all the commercial softwares, that grid is either open or closed. Binary, 0, 1. In ELSA, it's not like that. ELSA, these are open. These are survey element. They are open. But these grids are proportionally open. So this part of the fracture is open. This part is not open. So what it does, it has a survey elements, and these survey elements, one grid behind the fracture front, and they're tracing your fracture, where it goes, and they calculate the velocity of the fracture growth. So the calculation of the velocity of this growth is a function of your leakage at the front, how elastic modulus is at this point, or stiffness, and how it's toughness. Because it's so many iterative, And the formulation also new. It's been around only 5 years, so no one does. So what's good about it? It has, you calculate the toughness. You can include the toughness in your model. And also, and you test it after this, because normally doing it in classes don't have time. If you change the grid size in this software, the shape of the fracture, pretty similar. But in the other software, if you change the grid size, the total answer is different. Yeah? You've done the fracture?
Yeah.
Yeah, it's totally different. That's not because we are good. That's because the ELSA model really is very scalable. You asked me.
No, yeah, because right now we're using ResTrack to model the fracture propagation. And yeah, and I know that what you're talking about that. And that is important to mention that because that is
How much ResTrack get from university? Do they charge you guys or that's for free?
Actually, I don't know if we pay, but we have that.
It's for free, but if you publish, you have to go through them. You cannot publish with this.
Oh,
Yeah, definitely.
They approve your simulation.
Because like normally you say like you don't want to give it for free, but there has to be some cooperation. You give it something to us.
Yeah,
But I've heard ResTrack provide like a lot of free licenses.
Yeah, but we have actually we have, but more than we have, but the question is this, no, because not only for political, but for unconventional, the idea is how we are going to create more fractures, how we are going to keep the fracture, and then we are going to get propans and to keep the propans for more time, a long time, and to keep that conductivity the same with a high permeability for a long time. That is the idea, because the permeability will be reduced for a long time
That one they do. That one they consider. I think they have a time factor in their model. I think ResTrack got it. You got it. That's the simplest thing to do. But yeah, like ResTrack. Actually, ResTrack got a person who, one of the developers of ELSA, but he came like 10 years after they had the software. Like, and normally these software is building by the students from the university, and then they want to commercialize it. What they do, they have a code, big code, which normally, I'm not talking bad, negative about all of them, but all of them pretty similar. The guy who coded, he coded like a PhD student, all right? He then created code in the way that can be commercialized in the future. So then they buy the viewer from someone. The investor comes and say, you go and buy this interface viewer. And that's what I want. The interface viewer is like you have to put notepad in it. And then they say, okay, now we go and commercialize. And the problem is, it's hard to change those sort of software like which is developed by one student or one student. The structure of the software is not capable of doing it.
Yeah, for the reason we try. Okay, we have the license, but we excite in it has to model. It takes more time, but the coding of. But I'm not a coder, but I'm a user. But as a user, for me, that is better to have a visualization. That's better, and excite. It takes more time to simulate. But I trust in that value more than the value. Right?
Yeah. You use Autotasker.
Yeah.
Oh, yeah, that's good. But yeah, none of them use ELSA.
No, but it's interesting just because the idea is that you said the more there's how you're going to analyze it. I think that it takes my attention. No?
Oh, okay. So these shapes, I'm saying, like these shapes, you have it. You cannot get these shapes with Gopher or ResTrack. You see, like flat thing goes, like you know, it goes wherever. Like flat thing, the rectangular goes. Yeah. And that's not because we are a good coder or anything. ELSA model have these survey elements that's tracking the front.
And just one comment that's important because in this case the problem with ResTrack or other syntax as well.
Yeah.
They are thinking that about the analytical models, PTM, KGB.
Yeah.
All that are horizontal, more than radial, no? Radial models.
Yeah.
But if we are working in, for example, in Irani,
Like a geothermal stuff.
Yeah, for geothermal, that means the model will be different. And okay, analytically, we can model that, but with a numerical simulator, all the times they provide me horizontal model.
Let's go forever.
Yeah, that is the main problem.
So, and this example, because you are concerned about geothermal, I do something for you. Maybe that's more interesting for you. One of the things we do, and that's because also toughness is like everything. You have a vertical to horizontal ratio. And in granite, it's huge difference. Like a toughness, open up this fracture and going up is totally different. It's like a permeability, okay? And all these suffers because it doesn't have it. And let's run it and then go the PowerPoints. So other thing we do different from other software is so come the next slide, and then we run from the bottom. So these are the different toughness ratio, and this is everything homogeneous, but I'll give the toughness ratio of 3 to 1, and you see it's once you give like the vertical direction toughness is higher in these granites on these strikes. And this is like homogeneous like granite. You see, you are more contained. It doesn't let you grow. And that's not because you're doing anything different. That's because you have a huge toughness ratio. Okay, now we go in the example 15. And the other thing we do different, that's why we're still testing it before we can give it out. On the proppant transport, we do
Right, that's
no example, open example.
okay. All right.
Forget about cohesive elements and those. Cohesive elements is also important for like geothermal. Forget that. Okay. Now go in the you open it already. Cancel. Go in the fracture stage. Go in fracture stage.
Where is it? Okay. Okay.
And go open the stage 1.
The pump.
Go in the pump schedule. So I give you Excel for example 15. Open that one. I send an email to everyone.
And you separate that isothermal and thermal part, right? In your software.
Yeah, we start with the thermal. We start with thermal like SAGD. Most of our clients initially was SAGD and those ones, and there were no hydraulic software for like FCD and thermal.
Where is it?
Like CNRL software. We started
Where is
thermal.
the Excel, man?
Yeah, because this report that
Okay.
it was about
Oh, that was geothermal.
yeah, but
No, we have a geothermal section also on this software.
Yeah, because geothermal goes in the website is well.
that it was your.
Yeah, okay. Yeah, I teach a geothermal course. I use the software, but I'm telling everyone this part of the software gonna be dissolved in other parts. We just separate it because the problems in the geothermal is different. We want to do it separate and testing it, and once we realize everything's fine, we dissolve it in the other portion of the software. This is just because people complain about the graphs and everything. Example 50, open it. The Excel copy paste it here. If you paste it, copy, paste it.
No, I think what
Is the company is good?
no, I
No, I emailed it. Java emailed them.
Why you didn't send it, man?
Okay, make
Java
the
didn't-
Excel like this. Make Excel 0 to 11, 555, 0 to everything. Only do the profit 100, 200, 300 something. And
You can create Excel right now.
you can just create, just copy paste it, and give the Excel and send it. So then, because we only have one profit and one frac fluid, automatically shows frac fluid 1 and profit fluid. We copy paste it and then we go and change the frac fluid. We only have one frac fluid and profit.
Prepare.
And now run the frac. For simulation, practice. One computation. One computation. For fracture simulation. So practice the second.
Okay, okay, that's right.
Yeah. So for problem, we do CFD now, but I see a lot of bugs we're fixing it. So that's why we say everyone want to use share. Hold on, let us finish the CFD bugs then, because the problem transport now show them the go on the results.
Good results.
Because there is a lot of complaints about this problem transport. The one you show here is like a simple problem transport, like everyone doing.
Errors.
But the CFD one
Results.
is we do the particle
These are-
tracking. No, go on the well. It's the well waiver. Go on the fracture. And just move this. Move it to the end where like. So you see the fracture drop. And go on the problem, for example. On here, like you have on the top fracture dimension, it's stress intensity.
You can change a different type of profile.
Yeah. You have to define, you add your problem here. And then in that one, you only have one problem in the, go in the well again, go in the well,
The what?
go in the well,
Yeah.
go in the well, in the, like the,
Okay.
the main, on the main, here, down. Go on the well one, open it, go in the schedule, go on the practice schedule. Open it, go on the hydraulic fracture, go on the pumping schedule. Bracket state on the bottom. Go on the stage one, open it. Go on the pumping schedule. Now you can drop part. Like you added only one track to it and one preparation or one problem, so that's only drop one. You can drop part at any time you want. Okay, go now, results, see the fracture.
Results.
Yeah. But CFD, let us finish the CFD and then start. Like it's probably 2 months away, 3 months away. And then that would be the good combination, having the some ELSA model on the plus the problem transfer. Go see the problem on the tab here. So it shows the problems go down. You put a very heavy problem. Yeah, so that's it. Let me go on. If you're still interested, I teach you guys how to do the multiple thing with the multiple simulation and get the range of data and the result. You want to do that? We still have time?
Do you want to?
Guys?
This guy's tired. But yeah, I send you the example. But let me
Yeah,
show
you
you
can
the.
Yeah, you can send us the example.
I send you guys. Yeah. So you also have a cohesive element. So that's something like for geothermal aspects. So the thing is, like for the reservoir properties, I didn't show you guys. On these wells, you come over here. This is the part I tell some of you guys, if you guys have something that can be really helpful for us. So the software get the density logs and all of those guys and use this type of equation to convert the elastic dynamic to a statics. So then you have these properties populated here, like hydromechanical.
What is it about? Gamma, okay.
These are gamma, and this is the properties they use it. Okay, this is elastic, and this is Poisson ratio, and this is the fracture toughness. And those two are not attended in the class, but they say they are coming up with a static dynamic equation. So in this part, we follow the gopher structure. So we read all the logs and we populate everything, not like other softwares. But if you guys really can help us, like these are the equations built in gopher. We didn't find the better equations for the shale oil. So if you guys have any equation that can help us, you can put these ones and run it. So let me go through the PowerPoint for the Monte Carlo, and we're not running it for sure. So once you run it and you have the case ready, okay, we have example 12. I don't have example 12. Okay, I don't provide example 12. So you have example 12. When you open it, oh, that's Excel. Okay. So I go through the Excel example of how to do Monte Carlo simulation in Excel. If you guys are interested, you can follow that one. But in our software, you can go, there's a Monte Carlo tab here. And then you go there and you say, I want to do Monte Carlo. That's the results you want to see. But you can go and give all the variables you want to do, like MC fluid, if you want to do fluid change, you do the table of what viscosity are. If you go to reservoir, you do the thickness. Because lots of this part is for reserves company. There is one or two companies use us for just reserve calculation, and they want to do for different permeability. They want to see. And you just hit the perform Monte Carlo, and you get a chart like this. You get a chart like this. You can do many parameters, but if you do small amount, you get this. So the red ones is the one you history match, for example. And these are the properties you did not set. So normally you're trying to do your reservoir simulated has to be close to the green line, which is the average. So you can do as many as you want and let the software run for like 1 hour, and it gives you all those lines, and you can click on it. And once you click on it, it gives you this chart. If you click on the chart, it gives you the graph pops up on that location and give you theta and T2P. That's for reserves, if you're interested to do. Some people in the FCD world, they want to do different FCDs and they want to see how the performance is going to be. So, but mostly these are for smaller companies once they want to provide something to the bank for loan and those stuff. They use this. This is mostly being used in Canada. But you're running. I'll send you guys example 11 and 12. And we are open to do any help or, but it has to be mutual. If you guys want to use it, you have to give us, you have to help us in coding or like part of your PhD do something. Like, we're really interested to work with universities, not on money, but on projects. To trying to get the better models, and if you have something that you can add it on, like or examples like Mr. Al Hakim has it, and then it's a big software, but it's simple.
It's a lot.
It's
Simple,
simple.
yeah, simple, but it do a magic work, a lot of magic work.
Very simple. Yeah, I'm here tomorrow and 10 to 4? Tomorrow what do you teach? I said tomorrow is a short one.
Yeah. So,
It's just 1 hour. I prepared a 1 hour, 2 hour presentation.
yeah. So we will present and we can discuss something.
Oh, okay. Like what time you want to start? 10? Okay, good.
And then tomorrow.
Okay.
10 to 12.
Okay. Thanks everyone for coming, guys.
No, thank you.
Thanks for.
I think I will try to install my computer in my home because I have a Mac here. But I was.
Oh, don't do it on Mac.
No. But it was in the virtual PC. But I try to send an email.
Okay, sure.
Because As I mentioned, that is my interest was about
Yeah.
that part because that was I'm working on this part.
Sure. And everything you see, yeah, great